Well, a very, very good morning to you all, and thank you very much for coming along today to what we hope is a very special event that marks the end of the fourth round of the HSMA program. I always look forward to these events in particular because this is a great way in which we can celebrate, and it very much is a celebration, the work of the HSMAs over the last year. And you're going to hear this morning about some fantastic impact stories in terms of the way in which the skills that we've taught these HSMAs over the last year have translated into real world impact, real world change, and a real difference to their patient service users and their organizations. And that might come about as a result of direct impact from the project, and from whatever model they built and the results from that, or it might be that it's a wider impact where they've actually now built in these core skills into their organization. You're going to hear lots of different stories this morning about how this has worked. So really, this morning is all about the HSMAs, and we're delighted that we've got 16 presentations for you this morning, 16 fantastic stories of impact, and why a demonstration, I think, of why the HSMA program is so important. Excellent. Okay, so let's start by talking a little bit about the HSMA program. I suspect many of you who are here will know about the HSMA program, either because you're about to go on it, because I know we've got a number of you who have been following us for a number of years. But just to give a sort of brief overview and a reminder, if you like, for some of you. So the HSMA program, the Health Service Modelling Associates program, we set up back in 2016. My goodness, it's evolved a lot since then. But that really set the groundwork, that initial pilot program, to find out whether this idea of getting analytical staff or people who were interested in analysis or advanced computing or mathematics, who are working in health and social care and now policing as well, to be released from their usual role for a day a week for 12 months. Now that's actually changing for HSMA 5. We're launching HSMA 5 next Tuesday. We're going to go up to a 15-month program. This is mainly because the training course has now become so large that it becomes a bit intense during the training phase. So 3 months is not enough to contain our training now. So we now need a 6-month training phase so that you're not just permanently doing training and getting sick of the sight of my voice. So we have a 2-phase structure for the program. The first phase, which was 3 months for this program, but we'll be going up to 6 months, as I say, for HSMA 5 and beyond, is basically an extensive training course where we teach programming skills. We assume no programming knowledge, prior programming knowledge, operational research and data science methods. I'll talk a bit more about that in a moment. But then the crux of HSMA is the second phase. It's not just a training program. It's a training program where you then apply immediately what you've learned to something real world and important, and something that will have a real difference. So you get, as an HSMA, to propose projects, project ideas for things that you could tackle within your own organizations using the skills that you've been taught within phase 1. And we have a number of those, and we then filter those through, and we take a number of those forward. So we took forward 18 projects in HSMA 4, and 2 of them unfortunately had to cease in the middle, but we have 16 of them who are going to be presented today. And also, very importantly, this is a course that we are delighted to offer completely free of charge, and now we offer it entirely online, so that we open up to a national audience. So why do we do this? Well, the aims of the HSMA program really are to try and embed these operational research and advanced data science skills within health, social care and policing organizations. We want to try and increase the amount of evidence-based decision-making that takes place in those sectors, but also to develop the skills of people working in these sectors to be able to not only be aware of these things, but actually be able to do these things themselves as well. It's also really important that we create people who are ambassadors within their organizations, who can talk about the fact that these methods exist and what they can do to bring about real change. But a really important aspect, actually, of HSMA that's always been at the heart of HSMA back from when we had our initial pioneers, our 6 pioneers back in 2016, is that we develop and foster collaboration between health, social care and policing organisations. And we do that in a number of ways. But crucially now, with such large cohorts, we actually get them working together within the training, but also collaborating together on the projects. And we'll talk a bit more about that in a moment. And a really important point actually as well, particularly as our team Pencord is now very much an open data, open science team. A key part of HSMA is kind of pushing that vision and why we do that, and why we believe so strongly that free and open source approaches are so important in analytics. And we have an entire module dedicated to that and tools to support that and to enable people to collaborate openly. So I keep talking about operational research and data science. For those of you who are unfamiliar, operational research is basically just a fancy way of saying using sort of computer models and simulation and analytical techniques to try and help inform decisions about some aspect of the operational management of an organization. So an OR question might say something like, well, where are the delays in our emergency department processes and how might we reduce them? So we could build a model of the emergency department, find out where the problems are, and then test out little scenarios in the model to see what we think might help. Data science kind of comes at this from the other end of the spectrum, where you're led by the data. So it uses techniques such as AI, data analysis, to generate insights from data. So a data science question might say something like, can we teach a machine to predict when an emergency department is going to breach the 4-hour target, for example, using the data? So trying to unpick something within that data that allows us to do that. So the training program within HSMA 4 was over 140 hours of training content, by far our largest ever training offering, spread over 9 modules, starting from the introduction to this is the world of OR and data science, and this is how you code, and this is how you code in Python, this is how you code in R, and teaching that from first principles all the way through. So talking about open source and collaborative development, why free and open science is so important, modeling pathways and queuing problems, whole system modeling using system dynamics and network analysis, geographic modeling and visualization, where you place services, what happens when you relocate services, modeling behavior using agent-based simulation, machine learning, hugely popular in the HSMA course now, and you'll hear a lot of machine learning presentations this morning. Natural language processing, how we actually try and extract information using AI methods from free text data. Forecasting, loads and loads of different stuff, basically all the stuff that we do and we know about within the team dumped onto the HSMAs. But trying to sort of open their eyes to the possibilities and what can be achieved with these kinds of methods. And we deliver that via a combination of live lectures and group exercises via Zoom. We have our Slack, HSMA Slack workspace, which provides peer support to all of the HSMAs. They're all separated into peer support groups that they continue to learn with, little tutor groups throughout the training, and access to us as trainers as well. And then some sort of pre-recorded bonus stuff that we put up on the HSMA YouTube channel. It's important to say all of our content in the free and open source spirit is available free and open source. So any of you can go and watch our lectures and access our lecture content. So the project work in phase 2 is very much led by the HSMA. They manage the project, they own the project with their organization, it's their project. We are simply there as mentors to kind of provide advice and guidance and nudge them in the right direction. But these are their projects, and it's important that they have ownership of them. And you'll see why that's so important this morning. They're also supported by a workplace supervisor, someone senior in their organization, possibly the line manager, doesn't have to be, but someone basically who can support them and make sure that the stuff they're doing in their organization actually gets implemented and affects real change. During the phase 2, during the project phase, we have monthly learning set meetings where basically once a month, all of the HSMAs and mentors come together, basically have chat about what they've been up to. So they talk about the progress they've made, problems they've had, successes they've had, share ideas for new things they found out about that they're implementing, and they can sort of give and receive feedback. And they can also get some time to spend with their mentor. Now, because HSMA 4 was the first time we went so big with this stuff, that we had to change the format a little bit. So what we decided to do was to have the first hour as a kind of show and tell session with everyone. So a number of the groups would be selected each month to kind of show us something they'd done interesting that they'd done that month on their project. And then the second hour, they'd have some sort of one-to-one time with their mentors to talk about what they'd do next. So in HSMA 4, we also introduced something called the Trainee Mentor Scheme. This is a brand new thing we've introduced mainly because the HSMA program has got rather large since 2016, where we had our initial 6. We're now getting 3-digit numbers of people every year. And so we're still a small little team. We've grown a little bit, but still not enough to be able to mentor the scale of the projects that are needed. So we can deliver the training fine to hundreds, and we do. But obviously we need support to help with the mentoring. So we opened up something called the Trainee Mentor Scheme, which is basically open for people who may be academics in OR, maybe existing data scientists. They might be HSMA alumni. We've had a number of those that have come through the program. They basically get access to the same training as everyone else, but they tend to have a bit of experience in something. So they might have done some discrete event simulation. They might be very experienced in that, maybe not using the same methods we do. That's fine. We teach them that, but they've got a bit of experience in their past. Or, as I say, they may have been through the HSMA program and they therefore have got experience of being an HSMA on the program. And they get to share that experience in the mentoring process. And we've had some fantastic trainee mentors this year. We were overwhelmed with the interest of 11 trainee mentors that came onto the program. And it's been absolutely wonderful, genuinely working with them all and seeing them all support the HSMAs so fantastically well. And you see some fantastic quotes. It's really nice to read stuff like this because it as well as helping us, it's really nice to hear that this is something that they've enjoyed doing as well, and it's meant something for them, which is really important. I'd say for the first time ever, we really grew HSMA this year. So for the first time ever, up until HSMA 3, we were just running within our sort of funded patch of Southwest England. But for HSMA 4, we dipped our toes into the water of opening up to a national audience. We thought, well, we've had a few emails over the years about, when are we running this beyond the Southwest? So we thought, let's see if there's any interest. Turns out there's quite a lot. So we put it out. We had over 300 registrations of interest, and we took forward 80 HSMAs. Now this is a huge leap from the 6 that we had all those years ago. And we had 53 different organizations involved in HSMA 4. That's a huge thing, especially when we're thinking about collaboration and building collaborative partnerships. To have 53 different organizations involved in this program just this year is remarkable. For HSMA 4, so we delivered those 140 hours split over 23 days of training. And we mentored 18 projects, 16 of which you'll hear about today. And again, it's been fantastic to hear about the wider impact that the HSMA program has had for the HSMAs that have engaged with it, that really have enjoyed being part of the program, learning these new skills, and crucially, being able to then apply them immediately to something that's important and real world and tangible for their own organization. And as I say, it's been marvelous to hear their feedback about the course. I'd say each HSMA is split into one of 10 peer support groups. They're kind of tutor groups. They all work in all of the training exercises. They work in groups together and support each other right through the training phase. This year the theme was AI from movies and TV shows. So we had a lovely range of peer support groups here. they all worked fantastically well together, and it was great to see them collaborating so well with groups that came from very different backgrounds very often. For HSMA 4, we also introduced brand new training content, particularly around some of the core modules. So the open source collaborative development, we had a bit of a tutorial session around using some of the IDEs that we use in the course, a principles of FOSS and version control. I taught them Git. That was a learning experience for us all, I think. It was a learning experience for me in how difficult it is to teach Git. So we're actually changing that a little bit for HSMA 5. I've actually had to double the length of that training. It turns out you need quite a while to teach Git. For those who are aware of Git, you'll know why. We've also brought in some extra stuff into the modeling behavior module. So we talked about cellular automata. I blew their mind with some weird cellular automata behaviors. We had a fantastic guest lecture from Luca at UCL, one of our training mentors, who presented a fantastic ED model they developed using R. And we completely rewrote the machine learning module, which had been getting so much interest over the last few years and continues to do so, that we actually rewrote this. So we restructured it. We brought in a real sort of introduction to the concepts of AI. We talked about the ethics of AI, which is so crucially important when you're sort of going out and doing this stuff, and then diving into some of the neural network and non-neural network based approaches, as well as introducing our cohort to synthetic data, the way in which we can use AI processes to create fake data from real data. So good that you can't tell the difference. Something else we did this year was we set up a brand new HSMA resource website. The slides will circulate after this event, but the link is here, and that has lots of information about the program, and it's useful for anybody who is either on the program, because it's got lots of resource information, or interested in the program, or just interested in sort of data science and OR for health and policing and social care in general. That there's lots of information on there. We've also got our dedicated HSMA YouTube channel, which includes all of our lectures and past project presentations. So this event today will be recorded and will go up on the HSMA YouTube channel. And as I say, all of our materials are open source. So for HSMA 4, we can see the GitHub organization here, which has separate repositories for all of the training content. And we've also, for the first time, got a student GitHub organization. So this link here is where our students, our HSMA 4s that are talking today, will be uploading their projects. So you'll be able to go and have a look. Some of them have already done that, but most are in the process of doing that. So keep an eye on that over time, and those things will gradually be uploaded, and you can have a look at the stuff they've actually developed firsthand. Okay, so before I hand over to the HSMAs, I'm just going to take you through a bit of a dummy's guide to some of the technical stuff that you might hear about this morning. So our HSMAs aren't going to go into vast amounts of technical detail, but they are going to casually toss in things like, oh, I built a discrete event simulation, or look at how good my ROC curve is. So rather than sitting there thinking, what on earth is he talking about? I'm just going to give you a very quick overview about what these things mean, some of the things that you might hear about in a moment, what they mean. So basically, I've condensed down the first 3 months of training into 5 minutes. So this will be interesting. So discrete event simulation, some of you probably are already familiar with that, but it's basically a way for us to model queuing type problems, which are useful when we are looking, for example, at a patient pathway, and we want to look at the resourcing associated with that pathway and what might happen if we change the resourcing, or what might happen if we change the pathway in some way. So it's really useful for asking kind of what if questions about resourcing or process changes. And in HSMA, we use a package in Python called SymPy, and that's the package that we teach, that allows you to build very sophisticated discrete event simulation models. So an example discrete event simulation might be something like, patient arriving in ED, they have an activity over here which represents them being booked in, and that's got associated resource of a receptionist, and they queue while they wait for the resource, and then they move to the next activity, etc., etc. And we can all think of lots of examples within different sectors where this kind of modeling is really useful. Geographic modeling is another really important one, where essentially we're looking at trying to work out what the impact might be of locating or relocating services. So where might we place services based on where we know the demand is, or where might patients go if we were to close certain services, or where might we find people with a certain condition, for example. Network analysis is a fantastic thing that's really growing in terms of the team led by our colleague Sean Manzi, who's doing some fantastic work in using network analysis as a way to try and unpick and understand large-scale complex systems, a bit like the NHS. That's a large-scale and complex system, and it turns out it's really useful for this kind of stuff, just to get a real head around the kind of thing you can do. And it's all based on graph theory. And thinking about your graph as your structure of your service and the various nodes within that graph as the different services, and then mapping out how patients move between various parts of that system. So it's a fantastic opportunity to explore and better understand a large-scale complex system. As I said, natural language processing, a fantastic area with lots of potential, where we're trying to use AI-based techniques to try and automate the way in which we can extract information from free text. All that data that we've so long, for so long had to basically ignore, allows us to try and extract information from that. And we do some simple stuff in HSMA, things like name density recognition, being able to automatically extract people and places and organizations from our text. Being able to do sentiment analysis, where we can automatically identify whether the tone of a piece of text is positive or negative, or maybe neutral in tone, and things like relation extraction, where you can work out the relationship between different entities. Machine learning, which, as I say, is a growing area of interest for so many of our HSMAs and for us within the team, where we're trying to basically teach a machine to make predictions about something based on data that we feed it. It's looking for underlying patterns in the data to try and learn something so that it's then an effective predictor. And there's some fantastic work going on within the team. Mike and Kerry and Anna are doing some amazing work on the Samuel project, which is looking at using machine learning for making stroke thrombolysis treatment decisions, and some fantastic work going on there. Within machine learning, there's a lot, but I'm going to cover a couple of key things that you might hear talked about this morning. So when you're trying to teach a machine, you have this idea of train test splits, or you might hear train test validation splits as well. It's basically you've got some data where you say these are the features, these are the things that, a bit like columns in a table, this is the person's age, this is their BMI, etc. And then an outcome that you're trying to predict. Were they admitted to hospital, for example? And you need to segment up that data. So you carve out a bit that is used for training, and you say, I'm going to show the machine this is what it's going to use to try and learn from and find these hidden patterns. I'm going to carve out a bit for testing, which I'll hold back until it's fully trained, and then I can see how well it predicts on the test data. That gives us an idea about how generalizable it is, and it hasn't just learnt everything that's unique to the training data and is useless beyond that. And usually we carve out a little bit called a validation data as well, which is, while it's training, have a little peek at that every now and then to just get a sense of how it might do when it's unleashed into the wider world. You might also hear about a few performance metrics, things like accuracy. Accuracy is basically what percentage of time did the machine get it right. Here we've got an accuracy of 60%, where it correctly identified the color of the circle in 6 out of 10 cases. I think that's pretty easy to understand. But accuracy on its own, whilst useful, can be a little bit misleading, because we can imagine, for example, a situation in which we have 99% of our data represents people who are not about to be admitted to hospital. 1% does, and it's the 1% that we're interested in. And if you're not careful, a machine can simply learn, well, I'll just say nobody's admitted because I'll be right 99% of the time. And that's why we don't just use accuracy to measure. So you might hear some of them talk about precision. Precision is basically where you're trying to get the percentage of correct predictions for the classification of interest out of the total number of times that classification was predicted. So here, if we wanted the precision of predicting blue circles, how good are we at predicting blue circles? Well, we've correctly identified 2 blues correctly here, out of the 2 blues we correctly predicted, plus 1 that we said was blue, but actually wasn't. So we've got a 66.7% precision there. So basically, how good were we at kind of finding them? Recall is kind of the other side of that coin. Recall, for example, here, if we want to look at the recall of predicting green circles, well, we say we've got 2 that we correctly predicted as green, this one and this one, and we take that over those 2 that we correctly predicted as green, plus the 2 that we missed that were actually green, which is this one and this one. So how many did we find, essentially? You'll also hear a little bit about ROC curves. ROC curves are quite complicated, and I don't have the time to fully explain them. But basically, it's a way in which you kind of there's something in machine learning where you have a threshold. The machine has a threshold at which it determines whether to make a prediction one way or another. So if you're trying to get a machine to learn whether the patient is going to be admitted to hospital imminently in, say, the next 6 weeks or not, then basically it'll churn out a number, and it has to decide whether that number represents they probably are or they're probably not. Now, by default, that threshold is 0.5. So anything above 0.5 is classified as a 1, and anything below it is 0. And that works fine sometimes. But particularly if you've got an imbalanced data set, you can actually find that varying that threshold can be much more useful. And so a ROC curve is a way in which you can essentially try lots of different combinations of that threshold and see how the true positive rate, the number of proportion of cases that you're correctly identifying, you're saying it's positive and it is positive, against the false positive rate, which is the proportion of cases that you're saying are positive but they weren't. So if we have a look at a ROC curve, I flagged this up because you're going to see a few of these this morning. Basically, we have this kind of graph here. We've got true positive on the y-axis and false positive on the x-axis. So the bottom left is basically where both true positive rate and the false positive rate are 0. So this basically happens when your threshold value says that nothing is positive, which means you never pick up cases that are truly positive, but you also never say something's positive when it's negative. And then the top right is kind of the opposite of that, where the both the true positive rate and the false positive rate are 100%. This is basically when you set your threshold so that you say everything is positive, which means you get everything right when it is positive, and also everything wrong when it's not positive. So you're 100% right on the positive and 100% wrong as well. And then basically everything in between is these different values that you're testing. But the key takeaway that you need to have from today is bigger curve above this line is better. So this line represents rubbishness. That's random. That's no better than random. Okay. If it's below the line, it means something's gone wrong in your model and you're predicting things the wrong way around. So hopefully we won't see any of those this morning. And apologies to anybody if they do present a ROC curve that's upside down. But what you're looking for is a curve up here, and we want more of this area up here. And so we're looking at an area that stretches up to the top left as much as possible. And that indicates that there's good performance potential from this particular model. And you may hear them talk about the particular area under the curve that they've calculated. So an area of anything above 0.5 is basically better than that randomness in the middle. And an area of 1 would represent a perfect model that it will correctly pick up all of the positives and all of the negatives 100% of the time. That's very rare. I don't think we're going to see any of those this morning, unless they're keeping things from me. You'll also hear a little bit of talk about neural networks. Neural networks are complicated, but they're basically a way in which we can have these things called neurons, which take in some input numbers. They do a weighted sum on them. So they add them all up, multiply them by a weight across this connection, chuck them out to something called an activation function. which does something with that number. And then it back propagates and checks the error. How good was the number I came out with here against the number I was looking for? And a neural network is basically just those, but all joined together in lots of different layers. For the purposes of this presentation this morning, you can think of them as little magical black boxes that essentially you chuck some numbers in and it does some magic in the middle. It's supposed to emulate what they was originally conceived as a way to try and emulate how the brain works, with its neurons firing off in different ways. It does some magic in the middle and then tries to predict something at the end. Turns out neural networks are absolutely excellent for a lot of problems. Nobody fully understands quite why they're so good, but they are. And so you will hear a little bit about neural networks this morning. Think of them as little magic emulated brains. That'll do you for this morning. Obviously, if you're coming onto HSMA, you'll need to know a little bit more, and we'll teach you a bit more about that. So I'm going to stop talking there and just say finally how absolutely immensely proud I am of all of the work of the HSMAs this year. As ever, they've delivered fantastically, some fantastic presentations, and as I said right at the start, today really does represent a celebration of them and what they've achieved, and their work today. So I hope you enjoy the presentations that are coming. So apologies, we've overrun very slightly, but we've got plenty of buffer built into the day. So as ever, if there are any questions, pop them in the chat and I will endeavour to answer them as we go along. But at this point, I'm going to stop sharing my screen and then imminently stop talking. If I can ever stop sharing. Why is that not working? There we go. Fantastic. Okay, so let me bring up the itinerary and we'll crack straight on with our very first presentation today. So first up, we've got Martina and her team who are going to be talking about some fantastic work they've done around patient-initiated follow-up, and trying to support the elective backlog recovery, which is such an important issue. So over to you, Martina.
Thanks, Anne. So hi, I'm Martina Fonseca, and we're here to talk about the project, the role of patient-initiated follow-up and digital outpatients in supporting the elective recovery. More specifically, can we better size the potential of these interventions to help clear the backlog? So this is a project that me and fellow student Shashan have worked on, and Alison Harper was our mentor throughout this project. So just as context, as you all know, the pandemic has had a considerable impact on health services, particularly elective care in England. As of June, over 6.5 million people were on the waiting list, and under 65% of those were being seen within 18 weeks. So NHS England and services are actively working on the recovery phase, including a multi-year plan to address that. So patient-initiated follow-up, as well as advice and guidance, are two digital interventions that are very much present in that. Advice and guidance is where one clinician asks for advice from another, usually through a digital means. So this can mean that, for instance, a GP might be able to ask for advice from a consultant, but avoid an onward referral that would have been unnecessary. Patient-initiated follow-up, which can be both for acute or more chronic patients, is where instead of regular scheduled appointments, you are flagged to be able to trigger an appointment as and when needed, based on your individual needs. So there's a large number of benefits on PIFU, but the ones I'd highlight here is that time spent otherwise on those patients that are well can be repurposed for more complex patients, or to help see those new referrals and hence help clear the waiting list. However, it's a bit difficult to size what the impact is, especially over the years. As such, we decided to, based on our learnings of HSMA around Python, discrete events, systems thinking and problem structuring, to try and size this impact. So we use discrete event simulation to look at what would be the effect of different proportions of patients going onto PIFU pathway and the rate at which they might initiate those requests, and as well the use of advice and guidance, and then see how would that resource that is redeployed help, for instance, to clear the upstream waiting list for new patients. So we focus on rheumatology. Why? Because this is a specialty, namely with very good clinical evidence on PIFU. Namely, some randomized controlled trials show that over 6 years, you'd have about 38% fewer visits than if you were in that traditional scheduled follow-up. As well, it is a specialty that is mainly outpatient with very long-term follow-up. So for instance, here you can see for a subcohort of those referred 6 years ago, the number of appointments you get over a 6-year period.
Okay. I'm going to present a simplified version of the PIFU pathway in rheumatology. So when patients are referred, they will queue for their first outpatient appointment. Some patients will only have the first outpatient appointment. Therefore, they would be suitable for advice and guidance, which is a pathway where patients' issues could be addressed by the GP and without any onward referral. For most patients, they will queue for the first outpatient appointment and then also follow-up appointments. When the patients have been in the system for a while, they will be given the option to join the PIFU or not. The PIFU pathway and the traditional pathway are similar, but patients in the PIFU pathway tend to have less frequent appointments. They happen around like every 7 months in the PIFU, but about like 4.5 months in the traditional pathway. And all the patients will only be followed for a certain period. After that, they will be discharged from our simulation. The advice and guidance and the PIFU are the two interventions in our simulation model. Next slide, please. The objective is to identify the impact of interventions on patient waiting times and the waiting list size in rheumatology. So therefore, we have 3 key performance indicators: referral to treatment waiting time, referral to treatment waiting list size, and the occupied resources. In terms of the method, first we build an illustrative baseline case, so while intervention is not implemented, and then we did what-if test scenarios, which vary by the proportions of patients using advice and guidance as well as PIFU. We simulated our model for 8 years. By the end of year 5, the interventions started, and the patients were observed for the next 3 years, and the 3 KPIs were measured in the last year. Next slide, please. We used the SimPy package in Python for the modeling, and the time unit is 1 day. The capacity is measured by the number of available appointments per day, and we did the replications for 30 times to improve the accuracy. We also assigned different priorities to different kinds of appointments. For example, the traditional and routine outpatient appointments were given the first priority because they are normally pre-booked by the service providers. On the right is a summary of parameters used in our modeling, including the baseline values, the distribution type, as well as the data source. Next slide, please. This is the result for our baseline case. As you can see in the plot, the median waiting time for referral to treatment is around 7 to 8 weeks in the beginning, and then it gradually increased to around 11 to 12 weeks at the end of the observation period, so which is more or less representing what's happening in practice. The median waiting time of rheumatology in February 2022 is around 11 weeks in England. Next, please.
So these were the what-if scenarios that we looked at. So there are all perturbations to the baseline case. So we had some scenarios where we included a PIFU decision. So these first 4 basically have different portions of patients going to PIFU, so 10, 20, 30, or 50%. Then we had one scenario that also had 20% going to PIFU, but we were a bit more conservative in saying how much less there would be triggering of appointments compared to the traditional follow-up. And then we had two scenarios where we had advice and guidance, one without PIFU, so where we said 15% of all first appointments could be avoided. And then the second one where we considered both that effect of 50% on advice and guidance and also 20% of those with follow-up going onto a PIFU pathway. So this is the example. So the first plot, these show the median waiting time over the 3 years of our simulation. So this is the graph that Shashen already showed for the baseline. So for instance, on the right-hand side in blue, we have, if we had 20% on the PIFU pathway, you could see that this would, in our simulation, stabilize the waiting list at around 8 to 9 weeks. And we had an example a bit with a more bold assumptions of 50% on the PIFU pathway, new patients. And you can see that over the 3 years, this starts to reduce the median waiting time in the waiting list. So this is actually showing the KPI for all the various scenarios I mentioned, but it's just the waiting time in the last year rather than in all the 3 years. So for instance, here you can see if we had sequentially 10, 20, 30, or 50% on PIFU, how that median waiting time in the last year of our simulation is reduced compared to the baseline. And for instance, here we have that other intervention, advice and guidance. So if 15% of all referrals were to be avoided, you can see the impact that has after 3 years of having that continually implemented. So to conclude, so our aspiration and from the learnings of HSMA is to continue advocating for pathway and behavior modeling, both in decision-making centrally and also at an integrated care system. So we're hoping that these use cases and the open source data can contribute to that. There's a lot of opportunities, both in terms of digital pathway redesign, the personalization agenda and issues around health inequalities, and also in elective and non-elective recovery. So namely for me, actually, it helped me, the skills I gained to tackle a question that was asked about ambulance resourcing models and the ambulance queuing times, where I was able to then use a bit of discrete event simulation to create a quick toy model to explore some what-if considerations. So we have worked on aiming to continue to work with a number of NHS England teams and also with analytical colleagues in terms of just sharing knowledge and ways of disseminating this. Some direct downstream opportunities include there are other musculoskeletal, of which rheumatology is part, conditions that could be explored or parts of the pathway, including primary care. Also, actually, PIFU is being implemented across most elective specialties. So you could think of generalizing this model so that you could apply for other specialties where PIFU is being implemented. And there's also opportunity to create a more operational model for direct use by service planners or operational managers in terms of the benefits. Yeah, this is just an example of how such a toy model could look like, where you could vary the percentage going to PIFU. And yeah, we're currently engaging with looking how that could potentially look like and what the personas would be for such a tool. And yes, finally, we'd just like to thank everyone that has helped us throughout this, and feel free to contact us or have a peek at our project. Thank you.
Fantastic. Thank you very much, both. And that was an absolutely fantastic presentation. It's so amazing to hear about the staggering results you got, and also to hear about the fantastic work that you're planning to do with this. And this is a great demonstration of why we love HSMA as a means of doing this. So fantastic. Thank you. So just as a reminder, do pop your questions in the chat, and our presenters will answer them as they go along. But we're going to move swiftly on to Andy next, who's going to be talking about some machine learning work he's been doing to look at predicting hospital admissions and length of stay for respiratory conditions.
Yeah, thank you. Hopefully you can see and hear me okay. So my project is aiming to use machine learning to predict hospital admissions for respiratory conditions and also length of stay. So first question, why? Because pre-COVID, hospital winter pressure is almost exclusively respiratory conditions. This is bed demand, beds in use from respiratory conditions pre-COVID, really obvious winter spikes. COVID obviously changed everything. We've had 2 winters where we've not had the usual spikes in flu and pneumonia. And yeah, we've shown before that actually the increase in total beds used in winter can be almost completely explained by beds in use by older people over 65s who have a long length of stay with respiratory conditions. And that affects the hospital all the way throughout. This is an example of all types for our performance over the long term. Real seasonal pattern with worse performance in the winter over a downward trend. COVID actually made performance improve at first when there was far fewer attendances and lots more empty beds. But then after a year or so, performance has worsened, and in summer 22, England ED performance is in the summer worse than it's ever been in the worst winter. So if, as some people in the news this morning are fearing, this winter we get the re-emergence of flu and pneumonia and have a bad winter potentially on top of COVID, then we'll be in a very challenged position. So there are some known primary care interventions which can potentially avoid some of these admissions. So, but if you've only got limited resources, you've got to know where best to focus those interventions. And we did in 2020 work with an MSc student from Lancaster University, beginning to have a look at, from the information you know in primary care about patients, how might you best target the ones who potentially are going to get admitted and stay a long time. And this project aimed to extend that work. So excuses first off. Time constraints, work in domestic meant I've done far less on this so far than I intended, hoping to develop it more. But I've done very limited literature search and stakeholder engagement, and as you'll see, done less modelling than intended. But it's been useful preparatory work. Few other challenges. One of which is that because this is a preventative type of model than a diagnostic one, any interventions that are already happening or ones that are proposed would change the model, which give you challenges around interpretation. So, for instance, if there's already interventions targeting people with on a COPD register, you might think, oh, that they aren't. Not many of those are being admitted. We don't need to focus on them. Whereas in fact, all you're seeing is that current interventions are working well. There's also extreme ethical issues to take into account. Whenever you're targeting anything, you are essentially rationing care. So there's ethical questions around that, particularly about equity, and there's dangers of machine learning models embedding any current bias. So would have to be careful of that for any deployment, and particularly using neural network models in particular, rather a black box. So as Dan explained, so the limited explainability also will give you potential challenges around showing that you're not proposing an inequitable solution. Various information governance challenges as well. We're quite restricted on how we can link and use primary and secondary care data, as I'll explain. There are potentially some other data sets which might also be useful, but I've not had time to investigate those. Big challenge around the data is, as I said, COVID changed everything. So because I'm looking at non-COVID admissions, I'm looking back to admissions in 1920, and frustratingly, because our primary care, we're only allowed to keep a snapshot of the data. We've only actually got data for patients who are alive now. So the model currently is actually predicting people who would have been admitted in 1920 and then survived another 3 years. So that's a big limitation of the current model, but it can be changed when I get more recent data. Also, there's an issue in that the long-term condition flags are actually as of now. So you're actually maybe put on a register after the admission, not before. There might be a way around that, but again, not had time to implement that. So as I say, this has largely been a learning exercise for me now to be able to do this in more depth when we get more recent data from this winter. Learned lots of things about actually setting up a model and doing some machine learning and how to present some of the results. This is just the first step, was replicating a logistic regression model, which has the benefit of much better explainability and also helps to deal with features that are closely correlated. So for instance, if you just do a simple tabulation of the data, some things you'd expect, like if you're on a COPD register or if you're aged over 90, you're more likely to be admitted. But there's some other things in there that may be a bit of a surprise, and also some things that aren't in that top list that you might expect. Whereas if you do a logistic regression, it takes the things into account together. So confirm some things. So if you are on the COPD register, you're 5 times as likely to be admitted, everything else being equal, as you will be otherwise. Age 90, 3 times as. And then asthma, which was way down here, if you just do a simple tabulation, where you take into account age and everything at the same time, you can see, as you would expect, more likely to be admitted for a respiratory condition. Learning disability, mental health, quite high here. Was initially surprised me, but I think that's to do with Down syndrome. And also on this model, deprivation wasn't in. That you wouldn't, just from doing a basic tabulation, you wouldn't think deprivation was that important. But when you do a logistic regression, you can see actually that 60% increased chance of admission if you live in the most deprived 10% of the country as the least deprived. So because that interacts with age and so on, that doesn't show up so easily if you just do a basic tabulation. So some work on creating neural networks. One of the points is that it's a very imbalanced data set. So as Dan mentioned, that gives you some challenges. So experimenting with techniques, because I've got a very large data set, I was able to use undersampling to produce a data set where 5% of the people were admitted rather than just 1%, which gave me the best trade-off between precision and recall in doing the model. And with very, very little optimization, the neural network, without telling it anything, just giving it the same features as the logistic regression, produced pretty much identical results, which was a positive start. It didn't better the logistic regression, but I think that's because all my features are trues or falses, binary features. So there's limited chance for the neural network to outperform the logistic regression. So as explained, less than 1% of the people in the test data set were admitted. So accuracy, as Dan said, isn't very useful. You could get 99% accuracy just by saying nobody gets admitted. This is, Dan showed a ROC curve, so it shows that even my first basic model is considerably better than just tossing a coin, but it's not great performance. But one of the challenges of these ROC curves is they're not particularly easy to interpret. So this is an alternative way of presenting the results that I think would be more useful if you were actually aiming to target interventions. And thanks to Stephen Ashmead, another one of the HMSAs who had a similar sort of chart. This is slightly different. This is cumulative, but this is saying if you target a certain percentage of patients, what would be the proportion admitted? So for instance, if in this size of data set you targeted your top 5,000 according to the scores that the model gave, 10% of those in the test data set were actually admitted, as opposed to less than 1% of the whole population. So the model's doing something in terms of prediction, but because we've given it a very limited feature set, not as much as I would like it to. So lots more work I'd like to do, mainly putting more features in, not just binary features, give the neural network chance to do more. I've not yet actually used the models to predict length of stay, which is a critical thing. Normal risk stratification is generally just the chance of admission, doesn't take into account the length of stay, which really affects the impact of the hospital due to bed demand. I'd like to use various methods to try and understand if the neural network does outperform the logistic regression, which features are actually contributing to that. So you could perhaps do a hybrid model where the neural network would suggest things that you could build into your logistic regression to maintain some of that explainability while getting the extra power. And crucially, using more detailed care history for prediction. And one of the thoughts further down the line is this is a theograph. So this is a human readable form of a patient's interaction with different care settings, primary, secondary, and other care. I'm imagining us making a much simplified version of that for each patient, and then using the kind of neural networks that recognize images, see if it could detect patterns in that history. So, for instance, it could be that a series of short admissions tend to precede a long admission. So that would be the further down the line. I was also asked just to mention a few other side projects I'd done using some of the techniques from the course. This is a bit of using network analysis. This is just something just showing ward moves, so you can look at all the ward moves in a particular year and see which where moves were from one ward to another. So that's been useful. And other people are going to talk about queuing problems. yeah, this is just an example of looking at number of patients in a ED department at a point in time, pre-COVID and post-COVID. So you can see these departments far busier, far more people in the department at any point in the week than there were pre-COVID. And that's even though actually attendances were only a very little bit higher. And if you look at the average congestion over time, you can see how it grows and grows and grows. So onset of COVID, departments were very quiet. This department had an average about 19 people in the department. It increases very slowly, less than one patient a week, but over 18 months, you end up with a department that's 4 times as congested. So that's just the point that other people will make in the previous presentation did about if you've got a system which doesn't have the capacity to deal with arrivals, then even a small deficit can lead to gradually increasing queues. So thank you very much.
Thank you, Andy. That was fantastic, and again, great to hear about some of the other work that you've been doing as well, and how your skills are spreading, and some fantastic ideas I think you've got for future work on your main project as well. I think that'd be really interesting. Brilliant. Thank you. Okay, again, questions for Andy, please pop them in the chat. But next up, we've got Alice, who's going to be talking about some fantastic work she's been doing around looking at the effect of pre-booked appointments in emergency care.
Perfect. Thanks, Dan. Hopefully you can hear me and see my screen okay. So yeah, my name is Alice, and I'm going to be talking about my work on the effect of booked appointments on waiting times at urgent treatment centres specifically. So just to start with a bit of background, so the NHS 111 started out life as a simple telephone health advice service, but thanks to a lot of work over the last few years, it's now much more embedded in the system, and call handlers are able to direct patients towards services that are near them that will be able to meet their needs, and even in many cases book them into a booked appointment slot at those services. And there's now an ambition that 70% of patients who are referred to emergency departments by NHS 111 should be given a booked time slot to attend. So it's hoped that this will make things more convenient for patients, but also help emergency departments manage demand and even lead to improved waiting times. But there's lots of questions about kind of to what extent that might improve waiting times and what the mechanism might be. So that's the question my project was aiming to answer, and I used discrete event simulation to try and answer that question. But you may have noticed I'm focusing specifically on urgent treatment centres, and that's because in an emergency department, it's well known that most of the time, waiting times are caused by delays admitting the patient to an acute hospital, whereas urgent treatment centres are intended for patients who have an urgent care need which isn't life-threatening. So patients tend to have lower acuity, and a lower percentage of them need admission to a hospital bed. That makes them easier to model in isolation. So that's why I focused on this case. Also, there's this handy document of principles and standards which set out, in theory, some of the commonalities across these services in terms of things like opening hours and prioritization of patients. And worth noting here as well, the model that I was intending to build was a sort of generic UTC model. I wasn't focusing on one service in particular. And the data that I was using the emergency care data set, and I took urgent treatment centres from that data set based on the data quality they had. So it's a generic model. So the first thing I did was look at, for urgent treatment centres where booked appointments have already been adopted, has that had a positive impact on performance? And by performance here, I mean percentage of patients admitted, transferred or discharged within 4 hours of arrival. So I looked at the latest data at the time, which was January 22. And this data includes UTCs and also other department types which are similar to UTCs. So only about 5% of appointments were booked in the data, but this did vary by trust. So you can see you've got one trust over here where for these department types, 100% of appointments were booked in advance, whereas many 0% of attendances had a pre-booked appointment, and you've got a bit of a distribution there in between. Average performance was better for booked attendances, so 99% of patients was admitted, transferred or discharged within 4 hours, compared to 97% for unbooked attendances, and that was statistically significant at trust level. but there wasn't a significant correlation between the percentage of attendances that were booked and the overall performance, which you'd kind of expect, because when you've got such a small percentage of attendances that are booked, you wouldn't expect that to have a significant impact on the performance overall. But then there's this natural question. So if the booked percentage were higher, would this lead to a noticeable improvement in overall performance? So again, that's kind of the question that I was trying to answer. So the first thing I looked at was how are booked appointments going to affect the profile of arrival times. And on the left here are the scenarios I ended up considering in the model. You've got the current situation. This is specific to UTCs now, so there's a slightly higher percentage of attendances that are booked, and that's this black line on the chart. So you can see in the current situation, you've got a peak in attendances around mid-morning and lower attendances in the early morning and later in the evening. And I assumed that the booked slots available would have a flat distribution. So as you get up to higher percentages of attendances being booked, you get closer to that flat distribution, and the number of patients coming in to the service is more constant throughout the day. And I will just note here, I've considered percentages all the way up to 100% of attendances being booked. That's not to say that that's going to be realistic for all services, but I did want to investigate that situation as well, just to get a fuller understanding of the system. So the next question I kind of asked was, what actually happens to patients when they arrive at these services? So again, I used the emergency care data set and used lots of process mapping to sort of try and unpick this. And you can see this flow to the right here represents the fact that as I was looking in more detail at the data and the data quality and excluding records which didn't look realistic, I ended up at a more simplified pathway. You can see on the left here, you've got lots of arrows going in all different directions and this slightly simplified view by the end. So for example, in this initial flow, you've got 11,000 patients who went straight from arrival to departure without any initial assessment, investigation, or treatment. But when I looked in more detail at those records, I could see that there was some evidence of sometimes treatment, sometimes investigation on those records. But the timestamp of when that had happened hadn't been coded, so it wasn't showing up in the process map. And since I didn't have full information about those patients, I was able to just exclude them. And that's how I kind of arrived at this simplified view. I also did some similar work kind of looking at the flow using Sankey diagrams. So again, initially, I'm seeing all sorts of loops of patients going from treatment back to initial assessment and from investigation back to initial assessment. And whilst this is likely to be realistic in some cases, in order to build a kind of stable model in the time I had available, I did have to simplify the system. So there are some kind of pathways that I have to exclude just to make the system manageable to be able to build the model. So as my kind of simplest version of the system, I arrived at this, where patients arrive, they have an initial assessment. Some then leave or are directed to other services, and I stop modeling them. So that's a departure. Some need some treatment and some depart after treatment. Others need further investigation, and then they depart after that. So that's what I built using SymPy. And I will just flick over so you can see the model running. So this script in particular, some of the parameters in the model I'm able to get from the data. Others I don't have data on. So for example, I'm not able to say from the data the average time it takes to treat a patient. And so I give the model the parameters that I do know from the data, and I tell it what the waiting times are. And then if I run this, what the code will do is choose some parameters, see how close the results are to the actual waiting times, give me an error, and then try some new parameters. And it does that until it's able to find parameters that give a good fit to waiting times. So the project is unfinished, but I have put some preliminary results here. And you can see as the percentage of attendances with a book time slot increases, we get this decrease both in the average waiting time for initial assessment and the total time in department. It is likely that these will change before the final results are shareable, but I thought I'd put that in there just to show some results. I've got some next steps here. In the interest of time, I probably won't go through these in detail, but I did just want to say a bit about the kind of impact of HSMA on me and the organization. And the most important thing to say is that it was a really enjoyable experience. I did have some kind of modeling and data science experience before starting the program, but it's been really useful, firstly, to get a bit of an overview of all the different techniques that are out there, so that when a problem kind of comes along, I'm able to say, okay, well, this is probably the type of technique that we might use for that problem. And I know where to look to get more detail, but then being able to do a project as well and kind of lead on that, present it to stakeholders and follow it through has also been a really positive experience. So yeah, that's it from me.
Fantastic. Thank you very much, Alison. Great to hear that you've had such a great experience on HSMA. So that's been really nice to hear, and fantastic, really promising early results that you're getting out of that model. So I can't wait to hear more about where that goes. And I love the way in which you've got your model set up to try and get it replicating reality as much as possible and automating that. So that's really cool. Excellent, thank you. Okay, so we'll move on to the last presentation of this first batch. So this is going to be Ian, who's going to be talking about using machine learning to try and predict violent incidents on mental health wards. So over to you, Ian.
Thank you, Dan. Just see if I can get the screen shared. Can you see that?
Yep, that's okay.
Perfect. Okay, hi everyone. My name is Ian Waring. I'm Information Development Manager at Birmingham Solihull Mental Health Trust. And my project was to use machine learning techniques to predict when violent incidents might happen on our mental health inpatient units. The project team in this case was just me, with support from my assigned mentor, Juan Adriano. Give you a bit of background first. So we're a big mental health trust. We've got 680 inpatient beds across 54 wards. And in 12 months before I started my project, we had over 4,400 incidents recorded on our wards that were classed as assault, violence or harassment. And about 1,650 of them were actual or attempted physical assault with varying degrees of either physical or psychological harm. So it's fairly self-evident, really, that reducing the number of these incidents is in the interest of our organisation, in the interest of our staff and patients. I do want to stress the vast majority of people suffering from mental health issues have no involvement in violence whatsoever before we go on. So the aims of the projects, the overall aim was simple: to see if we could reduce the number of violent incidents that happen on our wards. And technically the aim was to come up with a dashboard that would rank the wards in order from most likely to least likely to experience an incident. And that way our senior nurses could monitor the situation and experiment with various actions that could reduce the occurrences of violence. So I'd be doing this with a machine learning model using today's data to predict where incidents were going to happen tomorrow. I just want to take a minute to talk about ethical issues, because they played an important role in how I carried out the work, because there are lots of examples of machine learning projects with unintended consequences. So from the outset, I decided it would be best if I completely avoided singling out individual patients, because if my model ended up predicting, say, that patients of a particular ethnic group were more likely to be violent, then that could change the way those people were cared for, potentially negatively. So I decided to work only with aggregate data rather than information at individual person level. So there was no way for the model to pinpoint an individual at any time, and the predictions were all about what would happen on the ward. Spoiler, not all machine learning projects give you the results that you were after. And mine, unfortunately, is firmly in that category. So this isn't going to be a presentation where I show you a nice model and talk about the impact it's had on clinical services. Instead, I'm going to talk you through the journey that I took. So first steps. From a data perspective, I was coming at this project from a really strong standpoint. I've worked in our trust for a long time. I've got a really good understanding of the data we hold. What I needed to brush up on was violent incidents. So I got out there and I met with lots of staff around the organisation who had that expertise. My main aim was to learn from them and understand what the triggers for violence were. And there were some really strong common themes that came out. I was getting back a split between things that we did have data on and things we didn't have data on. So, for example, patients with certain diagnoses like schizophrenia are more likely to be violent. The level and experience of staffing working on the ward that day is a major factor. Or patients early in their stay are more likely to be violent because they're acutely unwell. And I could source data on that kind of thing, whereas lots of incidents are triggered by things that happen on the day. So, for example, if there's no staff available to take a person for a cigarette break, or somebody smuggles drugs onto the wards. I don't see those things happening in the data. And I hope you admire the word cloud there. These are the themes that came across, built in Python, thanks to instructions from Dan. So my data sources, I narrowed down to 6 main data sources we use in the trust to manage patient care, staffing, medication, incidents. And between them, there were thousands of potential features that I could plug into the data set. And the biggest challenge was limiting this down to the ones that might be most helpful. Not least because for each feature I'd add, I needed to write code to extract it, and then I need to look at data quality and cleaning it, and all of that takes time. So I initially went with 3 systems, our Rio system, Eclipse, and Inpatient Portal, leaving out staffing and medication on the basis that they'd be the most difficult to extract. So I cracked on with the technical work. Pulling data from all those systems took me a lot longer than I expected it to. I was only working a day a week on it. So for about 4 months, I was just using SQL to extract and prepare data from various systems. And there's not much to show you really, other than a lot of lines of code, and that doesn't make for a very exciting presentation. It was kind of lucky that I was working on my own on this project really, because this stage took a lot longer than I thought. And if I was working with others, they would have been waiting an awful long time to get their hands on any data. But on the positive side, I did all my data cleansing in SQL. So by the time I had something to work on in Python, it was looking like a nice, fully operational data set that didn't need much additional work. And I also did some exploratory work with the data, looking at relationships between features, but I'm not going to go into that now because of time constraints. So I was ready to start applying some machine learning. The type of learning I'll be using is supervised learning, where you give the computer a data set with examples of what you're trying to predict. So in my case, past examples of days where incidents happened or where they didn't happen, along with the associated data. The algorithms then detect patterns in the data that would be next to impossible for a human to identify by hand, and they learn from the patterns to make predictions. So based on the strength of these predictions, I can say whether my algorithm works or not, and whether it's going to be useful in predicting future incidents. I mainly use logistic regression and random forest, and applied cross-validation, which is a way of cutting up the data and retraining the models repeatedly, using different portions to get the best predictions. And the results were really, really bad, with almost no correct predictions at all. I didn't actually take notes of what those results are at this stage. I just thought, back to the drawing board, my data isn't good enough. So I spent the next few weeks adding a lot more data, most notably around staffing, using our staff and rostering systems to add a demographic makeup of our staff on our wards, amongst other things. It still wasn't everything, and I still didn't have time to include medication data, but I had significantly enhanced the data set. So more machine learning. I tried the same approach, logistical regression, random forest models. I was more careful about keeping hold of my records from this point. And you can see some early results I had in the corner here. I'm not going to go into all the detail about these individual measures, but you can see the accuracy looks really good, but as per Dan's warning earlier, it is misleading. And what that's telling me is my model's really good at predicting there won't be an incident, and terrible actually at predicting when there would be one. So precision and recall are better measures than accuracy for situations like this. But at this stage, I was getting divided by 0 errors for precision and really low scores for recall, and I wasn't predicting nearly enough incident days at all. So in scenarios like this, we've got an imbalanced data set, which means I've got a lot more days without incidents than I have with incidents. You can create new data that's similar to your real data to flesh out your data set. So Dan conveniently showed us a tool called Smote around this point, and that helps you create this synthetic data. So I used this to increase the number of days with incidents, so they're about equal to those without, and then I ran my models again. And you can see that the recall is right up here on the logistic regression model, which looks good, but actually it's massively over-predicting the number of incidents. And precision is quite high now for the random forest model, but still only a quarter of the predictions are correct. So you can see the predicted positive rate is really low. So the next job was to have a look at whether I could fine-tune my algorithms. So I used a method called OpTuner, and this automatically tries out a range of settings for your machine learning algorithm and tells you which ones perform the best. So using this, I was able to find the optimum hyperparameter settings from a random forest model and to apply them. And you can see in the scores here, the precision is a little bit worse, but the recall is much improved, and about 1/3 of the incidents were correctly predicted, but still a long way off the kind of figures I was looking for. So back to the data again. So at this point, Juan, who's my mentor, had some suggestions about ways I could reconfigure the data. And one of the big things I did was I was originally looking at all our inpatient units across the trust, but as you can see from this chart here, many more of our incidents are in our acute units than elsewhere. So I had a look at filtering the data down to just those units, and so I tried it with acute, with PICU, with medium secure, just to see if limiting it gave me better results. And in fact, the results came back worse, which was not what I expected. I also tried reducing the number of variables in the data set. I did things like combining features, so I had fewer age bands, fewer ethnic groups, and I tried various combinations of all of these things along with using smoke, not using smoke, tuning parameters, but I never really got any results better than anything I've shown you so far. And so there's some figures from one of my many trials here. So one last try. For my final attempt at getting some better predictions, I turned to artificial neural networks using TensorFlow. But despite taking quite a lot longer to run, they did not do their magic, and the results were no better at all. So I've taken an opportunity to show you an ROC curve here. Dan told us what to do earlier, so I won't go into detail, but I can tell you that this one is not good. So at that point, it was time to call it a day. I had had numerous attempts to get some predictions from the data, and eventually I had to conclude that it doesn't seem to be possible to predict violent incidents from the data set I was using. It's possible I might have been able to make better predictions if I had used person level data. So it might be worth another go at this, dealing with the ethical issues differently, say predicting for individuals, but then aggregating predictions and not showing person level. So organizationally, we did not get the benefits we'd hoped for from the project, but personally, I got a lot of learning from it, having never done any of this stuff before. And now my time with HSMA is over, I'm actively looking and keen to start my next project. So just to end with a big thanks to Juan, my mentor, and all his help throughout, to Mike for the Titanic notebooks, which were sort of the starting point for much of my code, and of course to Dan for the whole course. Thank you.
Fantastic. Thank you very much, Ian. And I would concur strongly with Richard's comments in the chat. I mean, this is it's really nice actually to hear about. I mean, it's obviously not quite so nice for you. It'd been great if the project had worked, but there's so much learning that you've clearly demonstrated in terms of the journey you went on through that project, and I think that's really useful. And you're absolutely right. It's really important that we hear about this kind of stuff, because machine learnings aren't the answer to everything, and sometimes you just don't have the data to be able to learn it, and it's just not learnable. And that's unfortunately just the way it is. But it's really good that you've not lost your appetite to go on and work on other things on that. Okay, so first up in this second batch, we've got Helen and team who are going to be talking about their work trying to improve the flow of patients through medical assessment wards in emergency care. So Helen, I will hand over to you.
Thanks, Dan. Okay. Is that displaying as a presentation?
Yeah, that's coming up fine.
All right, thank you, everybody. I'm Helen Young. I'm an advanced analyst for Nottingham University Hospital's NHS Trust. And my project was using discrete event simulation to look at improving flow through the acute medicine assessment pathway. So just to familiarise you all with the acute medicine assessment pathway at our trust, we have two major units known as AMRA and WB3. Typically, patients will enter the pathway either via presenting at the emergency department, or they can be directly referred into AMRA by a GP. They'll typically then either stay on AMRA for their assessment or move into WB3 for their assessment. But either way, after the assessment is complete, a decision will be made to either transfer them to a base ward bed elsewhere in the hospital, or discharge the patients directly home. Now, the problem is that patients are frequently waiting in ED for an AMRA or WB3 bed for more than 6 hours. This is a known cause of delay-related harm. So after speaking to stakeholders, they told me that they felt one of the major constraints was patients who are stuck on AMRA or WB3, who are ready to transfer out to a base ward bed, but are unable to do so due to a lack of availability of these beds. And they wanted to know, if patients were able to leave AMRA and WB3 more quickly, what would be the upstream impact on ED? And specifically, what would the system look like if all the patients on AMRA and WB3 were able to be transferred within 4 hours of their request for a base ward bed? So my proposed solution was to build a discrete event simulation, a business as usual model first that would attempt to capture current reality in the system, And then using that business as usual model as a template, I also built some what-if scenarios that simulated patients leaving AMRA and WB3 more quickly. And I'm aiming to use these alternative scenarios to explore the stakeholder questions. So the approach that I took to the modeling was as follows. I first extracted pathway data on all the possible routes through the system and what percentage of patients took each route. I then used a Python package to model the distribution of lengths of stay at each stage of this pathway. I built the simulation using SymPy. And as the simulation runs, when each patient is first generated, they're allocated a pathway, and this dictates their movements through the system and which areas they will go to. And then when the patient enters each new area, they are allocated a length of stay, which is drawn from these modeled distributions. So just to make it explicit, there are certain input variables that I kind of plug in directly into the model, and these are the ones on the left-hand side of this table. And there are also variables that sort of emerge from the properties and the interactions of the system as it runs. And it's these emergent variables that I'm using to validate my model against reality, and also to assess the impact of some of my what-if scenarios. And now I want to draw your attention to the fact that I've modeled length of stay into these two separate portions. The reason for this is, as I mentioned earlier, like one of the possible exits out of the acute medicine pathway is to be transferred to a base ward bed. Due to the fact that we see like a wide variety of patients with lots of different presenting problems coming through the acute medicine assessment pathway, this means they can end up almost anywhere in the hospital. And this, coupled with the fact that conditions obviously vary in the hospital day by day, means that it's very hard to put a fixed capacity figure on the number of base ward beds that are going to be available for patients to move into. So to sort of circumvent this need for a capacity figure, I've modeled length of stay in two separate portions, using the stay before their bed request to represent their clinical need to remain in the acute medicine pathway. And then the post-bed request length of stay is the time between their request to transfer out into a base ward bed and the time that they actually do move out. So essentially, this is kind of a proxy measure that reflects downstream flow constraints. So for example, if I want to simulate a situation in which base ward beds are more plentiful, I can decrease this post-bed request length of stay. Alternatively, if I want to simulate a situation in which base ward beds have become more scarce, I can increase this post-bed request length of stay. So this is the table of key performance indicators that I'm using to validate my model against reality and also assess the impact of my what-if scenarios. So these first four here are all occupancy metrics on WB3 and AMRA. And so in theory, if my arrival rate and my length of stay are calibrated correctly in my model, then these should be a close match between the model and reality. I've included this metric of the percentage of time that WB3 spends over 85% capacity, because management do have a stated aim to run WB3 at an 85% occupancy rate, although it currently, as you can see, spends most of the time over this. And then these two metrics here are reflecting conditions in ED, and these are the metrics I'm particularly monitoring to see the impact of any downstream changes in my what-if scenarios. So these here are my what-if scenarios, and these are all ones where I've effectively capped the post-bed request length of stay to a certain time limit, so that no patient is allowed to stay waiting on the ward for any longer than this. And if you remember, scenario 3 here, where all patients must leave within 4 hours of their bed request, was the scenario I was particularly asked to look into by stakeholders. And so my model suggests that if all patients were able to leave AMRA and WB3 within 4 hours of their bed request, then the patients in ED would never have to wait more than 6 hours for a bed on AMRA or WB3. However, in this scenario, I found that even reducing the post-bed request length of stay to no more than 16 hours would still dramatically reduce the number of ED 6-hour plus waiters, and it would also maintain an acceptable level of occupancy on WB3. So this scenario would free up space in AMRA and WB3. However, it would have a knock-on effect that patients would need to use around 25 more base ward beds per day to facilitate this flow. I'm currently still working on improving my model. Now I'm sort of a second iteration of it. The first version matched fairly well across many of the KPIs. However, one of its major limitations was that it simulated a steady state, so that occupancy and a patient arrival rate didn't really vary by time of day or day of week. So this graph here shows the occupancy over time for my latest version, which is a business as usual version 2. And here's the actual values from my historic modelling period overlaid. So as you can see, it now has a degree of seasonality, although there still needs tweaking. And one of the things I have found, unfortunately, is that after adding in this seasonality feature, my occupancy actually is less well matched than it was in version 1. So I think work's still needed on my version 2 model before it's credible enough to use as a foundation for any further what-if scenarios. So my next steps, I think, are to continue calibrating version 2 until all my KPI metrics closely align with reality. I'd also like to explore using alternative types of scenario. So far, I've only looked at capping post-bed request length of stay, but I'd also potentially like to look into reducing demand, potentially by diverting certain types of specialty patients elsewhere. And I also want to engage with my stakeholders again. I want to return to them with the insights I got from model version 1 and sort of discuss with them how we could start translating these findings into actions. So to summarize, I feel like the impact of my work so far is that in addition to all the learning that is just been an inherent part of this sort of modeling journey, I've also been able to start providing some concrete answers to things that were sort of fairly hypothetical questions around flow. I've been able to start quantifying the additional beds that might be needed to support this improved flow. And I've been able to bring back some of the insights from the modeling work to support discussions on how and where bed days could potentially be freed up. So that's almost it from me. I just want to thank my mentor, Alison, and obviously Dan for the HSMA course, and also my manager, Jürgen, for all the support he's provided during my time on HSMA. Thank you.
First of all, I said fantastic to hear about Helen's work and I think really promising results, and I can't wait to see where that goes with the second iteration of the model, because I think the first iteration shows so much promise. But now we're going to hand over to Shilpa. Shilpa's been doing some great work around modelling patient flow, again in emergency care, but this is looking at the urgent treatment centre and has some fantastic impact to talk about.
Hello everyone, hopefully you can see my screen. Okay, I'm Shilpa. I work at UCLH, and my project was all about optimizing the urgent treatment centre at UCLH. So a little bit about me first. So like I said, I work at UCLH within the business information team, support the medicine board, which includes emergency services. And I was part of the HSMA programme in 2021-22. And my mentor for the project was Dan. So thank you, Dan, in advance. So one of, I think there's been several DES projects already, so we probably don't need to talk about it too much in terms of the detail, but how this project really came about was the team that I work with are really interested to learn about what I was covering during the HSMA course, and we had a sort of lunchtime learning session to show them like one of the little sort of more simple models that we'd done during the course, and to sort of think about how we might start using some of the learning within our to support our teams operationally. One of my colleagues, he supports ED, and he had been talking to the urgent treatment centre team, and he suggested actually that we might use this approach to help them with this UTC redesign. So this was really exciting because they were really a supportive team. They really wanted to explore a different way of sort of visualizing and understanding what was going on in the urgent treatment centre. And that's where this sort of opportunity came from. So I would say that good engagement from the business is really important. So a little bit about UTC. I think Alice has talked a little bit about it already. Within UCLH, it's co-located within the emergency department and acts as the sort of front door to ED. I think approximately half of all ED attendances who are sort of low acuity or minor injuries will come into the UTC as a sort of walk-in, and generally they're seen by a GP or a emergency nurse practitioner. Many patients will be seen, will be seen in a consultation, and then will be discharged. some of them might need diagnostics, or, for example, blood tests or a scan, and then they'll have to wait for a second consultation before being discharged or admitted. So what are the challenges within the UTC? Well, in more recent months, there's been a falling target, a falling UTC performance against the ED target for patients to be seen within 4 hours of arrival. And there appeared to be a mismatch between the allocation of staff and the available consultation rooms. So this led to there being, many more patients waiting to be seen. And additionally, because some patients needed diagnostic tests, sometimes these were not, you couldn't order them until the first consultation was done. So they're waiting for those tests, and then waiting for the results of those tests, and then waiting again to be seen again. So all of this was resulting in sort of too many patients waiting to be seen. And at the end of the day as well, where there was a sort of lower staff night shift, there'd be what was thought too many patients waiting at the end of the day shift. So really the model needed to really to address what would be the optimum number of clinicians that would be needed to manage the patient flow for patients to be seen within the 4-hour target. And currently there was lots of debate about what that number of clinicians was. Additionally, they wanted to understand that if there was sort of variation in patient flow, so for example busy days, then what would be the additional resource needed to support that, the additional patients. They also wanted to explore different options. So for example, they knew that sorry, the slides keep flicking, apologies. They also wanted to know what would be the impact of sort of front loading diagnostics. So if you could order diagnostics earlier on, or maybe include a triage step, then how would that impact the waiting times? And that was the kind of flexibility the model needed to offer. At the same time, I did try to keep the model fairly simple. So for example, diagnostics were modeled as a sort of big bucket, even though realistically there's various types of diagnostics with different timings as well. So that was one of the complexities that we tried to make simple. Like others on the project, on HSMA course, I used SimPy package to build this discrete event simulation, and I modeled the patients as entities going through the system. Used log normal distributions for the different steps on the patient pathway. I did this using sort of data that we had from ED, and then just tried to understand what the best fit distribution would be for each part of the patient pathway. A baseline model was developed initially, where we looked at what the current staffing situation was, and also what the current timings were in terms of how long activities were taking, and then looking to see what the model said the performance would be against the 4-hour target, and then comparing that to sort of reality to say, well, that is right, that is what we think is currently the proportion of patients discharged within the 4-hour target. And then also we had data from sort of more busy days, and we were able to increase the patient flow going through the model to see whether that replicated sort of reality, and these kind of scenarios helped, I think, engage the operational teams and validated that the model was sort of simulating reality as best this kind of model can. So what did we do? Well, we tested lots of the scenarios that I talked about. We looked at putting in a triage step to divert some of the patients through that. We looked at varying the number of clinicians that were available, and the ED department was really willing to take on the suggestions from the model, and they decided they did need additional rooms to sort of manage the patient flow, and they adjusted their future staffing rotas as well to align with what the model identified as was needed. In terms of wider impact, it did also kick off a review of staffing rotas to sort of see how they could be better aligned to the findings from the modelling. And they are really engaged to sort of use a similar approach to redesign and rethink about other areas within emergency services to see how they can use discrete event simulation as well. So all in all, I think it was great for engaging the operational teams, but also provided evidence for what a lot of people already knew was the sort of right answer. But this sort of provided the evidence to make those decisions and to make that change happen. So yeah, all in all, really great project, and thank you to Dan for supporting as well.
But yeah, fantastic presentation again. Great to hear about the impact and the engagement. I think in particular with your project that this has had so much fantastic engagement from the stakeholders. So brilliant work, and really excited to see what you do next. Okay, so let's move on and move on to our next presentation. So we've got Matt and team now who are going to be talking about some fantastic work. They've been developing a tool to try and tackle inequalities and look at carbon emission issues, both really important issues within the NHS. I'll hand over to Matt and his team.
Thanks, Dan. I'm just going to bring the slides up.
Hello, welcome everyone. I am Anya and I've been working with Matt and Sally, and we're going to present to you our work on developing a service planning decision support tool to tackle inequalities and minimise carbon output. And this has very much been a cross-sector collaborative project where we have developed a generalisable tool, but we've piloted it with one set of data, and we're going to talk you through what we've done now. So the background to this project was to bring together three important priority areas for the NHS at the moment. Firstly, the inequalities agenda, where the NHS Constitution and NHS long-term plan include a mandate for the NHS to reduce inequalities. Secondly, the NHS net zero agenda, where the NHS has an ambition to reach net zero by 2040. And thirdly, the digital and transformation agenda. And we wanted to bring all of these three together and make a decision support tool to help service planners consider these issues. So what did we aim to do? We aimed to simplify the process of calculating patient travel carbon emissions and identifying health inequalities at scale for any service. And what have we done? Well, we've managed to produce a tool which is usable for any service, and we've piloted it with sexual health data from a service within Derbyshire. An overview of our methods. First of all, we imported the data and we've cleaned and processed it. We then run a machine learning model which identifies features and characteristics associated with patients who do not attend their appointments. Secondly, it runs an automated health equity audit which summarises unmet need for the service compared to the general population. And thirdly, it estimates the carbon emissions associated with patient travel to the service and then produces an automated report of all significant findings.
So the first thing that happens is we run the machine learning model for the unattended appointments. This analyzes the processed service data with 9 logistic regression machine learning variants. It then identifies the optimum one of those 9, and then it returns the 5 most influential features associated with patients not attending their appointments using this optimum model. It then undertakes an automated health equity audit for n number of conditions, as is meaningful for the given service data in use. For our project, this is based on contraception and gum, but it could be anything as relevant to the use case. The slide shows some example outputs, specifically using the dummy data that we generated from the automated health equity audit. On the left is a chart comparing the proportion of residents accessing the service by age range compared to the proportion in the same age range in the population. Significant differences are indicated, and on the right is a heat map showing relative concentration of unmet need for a given condition in the local authority in scope. For the carbon emissions modelling, on a geographical level, we used LSOAs, or lower layer super output areas, and assumed all patients were living in the most populous location within their resident LSOA. We used the Open Route Service API to plot where the clinic locations in scope were on the map. We used another OpenRoute service API to calculate the distance between each of these LSOA locations and each clinic. We then use published data on the proportion of people that travel by different means, for example, by car, bus, or train, as well as the carbon dioxide equivalent emissions for each of these travel means to estimate the carbon emissions created through patient travel to and from attended appointments for each clinic. We then produced the automated summary report, which was automatically created in MS Word, which identifies the top 5 features predictive of someone attending or not attending their appointment, the health equity audit showing the statistical differences between clinic attendees and the general population. It has the maps of unmet need for all reasons of attendance or condition modelled. It estimates the CO2 emissions from patient travel from their home to the attended appointments and back for the current service design, and also includes the appendices of all assumptions made, user choices, and a glossary of terms.
Okay, so I'm shortly just about to play a video of the tool running, and which will run through the code, and then subsequently the report that Sally's just described. It'll run through each stage, and each stage will appear in the top right to just keep you on track as to where it's at. There's a stopwatch that will be down here to give you an indication of the duration of each stage. And just to note, this is running at 4 times speed, just to fit it into the session we have this morning. So I'm just going to press play and then talk you through what happens. I should just say this is for a 3,000 record dummy data set, so the runtime does increase with increased data set size, mainly for the DNA machine learning models. So first off, there is the pre-processing stage. This is reading in the data set, cleaning the data set, and controlling for missing values. So where it's a text value missing, that's the word missing that's replaced, and where it's a numeric value, it's the median value that's used. Subsequently, the machine learning model takes place and has identified the optimum, how the health equity audit is completed using parameters from the user. The carbon emissions modeling is now taking place, so it's geocoding all of the clinics in scope currently, and now it's calculating the distance, so the 4,910 routes, possible combinations from LSOA, so those 10 in Derbyshire. The maps and now the report have been produced, and this is a report for a 40,000 record data set, which has been produced in under 11 minutes with all of the outputs from the model, from the various stages of the model incorporated, as you can see. So the maps in terms of unmet need or people not accessing where a prevalence rate hasn't been used, the DNA features, a glossary of terms, and appendices which include all of the methods that we've used, any assumptions that have been made in running the model, and any controlling taken place for missing data. Lastly, the charts from the HEA, all of which include significant findings indicated and acknowledgements at the end to all involved. So we were quite keen, we were quite fortunate actually. We had a public health registrar with our organisation during the work that was taking place for this project. So they'd undertaken a health equity audit manually, which gave us some comparative figures to sort of work through, well, what's the impact that one part of the tool could have. So with their input, we estimate that the HEA component is approximately 80 times faster using this tool than it would be to do this in sort of a more traditional way. So in real terms, that's about 15 minutes compared to 2 full days for one service. Now, as a provider of many services, we have approximately 35 service lines. So scaling that to an organisation, that's a sort of less than a day compared to 3 months of running these sorts of analyses to understand inequalities, or at a potential ICS level, so assuming 4 organisations of similar size, that's around 3 days compared to the best part of a year, factoring in annual leave. And I say hypothetical here because due to this sort of capacity barrier, this is one reason why these sorts of analyses don't often take place, and hopefully we can use this tool to get around that barrier and enable more insight more readily for inequalities present in services. So our next steps, we've collectively submitted a Healthier Futures Action Fund bid, which the outcome is TBC by the end of this week, hopefully. We intend to, hopefully, if that's awarded, use that to develop additional functionality. And that's sort of a couple of things there that we're thinking. One is, now that we've modelled the baseline emissions for the current service design, what we'd really like to get to next would be to look at, if we were to put a new clinic in a given location on the map, what might the relative impact be on both emissions and unmet needs that has been modelled for the service. So that could help with inform, actually, we have several different locations we might choose, which one might be the best one, taking into account the co-benefits or trade-offs between those two things. Fortunately for that functionality, we've already had a conversation with one of our other HSMAs on this programme who has kindly shared their code, and we might be able to use that as a basis in an open source way for that next step. Lastly, we're looking at repurposing the code for other uses. So for example, the machine learning part, looking at the DNAs, we were thinking, actually, could we repurpose that quite readily for other binary outcomes? So for example, looking at the demographics or features that might be associated with people who do or don't take up a particular vaccine, or do not wait within the certain target time, for example. So we've had a few reflections collectively on our experience with HSMA, and I think particularly because we're working across different geographies, different organisations, and all three of us are from different sectors. So it's sort of proof that not only can shared goals be achieved 100% remotely, but also beyond normal and traditional organisational boundaries. In terms of the course itself, the online format has been incredibly accessible. I don't think comprehensive content does it justice. I think the content's enormous, but it does allow you to pick areas of interest and clearly apply, as people are showing today, application to current challenges. Just want to acknowledge a number of people who've been instrumental in the work that we've shared today. So I won't go through them all, but particular thanks to everybody on the screen and everybody else who isn't, who helped with questions as well. Thank you ever so much for listening to our presentation. If you've got any questions, really happy to take them either in the chat or in the breakout, and I hope you enjoy all the other sessions.
Thank you, Matt, Anya and Sally. That was an amazing presentation. I have to say, if there was ever an award for the most ambitious HSMA project I've ever encountered, I think you would win it hands down. When you embarked on this project, I didn't think you'd get anywhere near it, but to see what you've achieved in effectively 9 months, to develop a tool that can transform work that would take a year into a few days is absolutely astonishing. So a massive well done. I think fantastic work, and I'm absolutely beaming with pride at all of these presentations as I sit here. Okay, so again, questions, pop them in the chat. We'll move on to the final presentation in this particular batch of 4. So we're going to go over, as we talked about earlier, we now welcome very much our policing colleagues into the HSMA programme. It's been a fantastic opportunity to link both health, social care and policing sectors. And I think this project is a fantastic demonstration of doing exactly that. So a number on the team are going to be now presenting about some work they've done around modelling the firearms criminality using geographic visualization. Fantastic.
Hi everyone. Our project is around the spatial analysis of violent crime. Our aim was to develop a model that could turn crime data into useful visual and analytical outputs from which analysts can draw insights for strategic analysis. Why? Well, the NCA, our National Crime Agency, which is who some of us work for, are tasked with providing a single authoritative picture of the threat to the UK from serious organised crime, and this is disseminated to partners in the UK and overseas via assessed intelligence reporting. We don't really have spatial analysis functionality at the strategic reporting level, which I think is missing, as there is a lot of regional variation in serious and organised crime. And if we want to explain change, we need to be able to describe those changes, which are often spatial. We wanted to create a model that could take crime-related variables with location information and undertake mapping and spatial analysis, especially identify clustering and hotspots that we can apply a level of confidence to and could use to complement intelligence analysis. We did have some challenges from the outset, which impacted how much we could achieve. The biggest one probably around access to NCA generated or restricted data. And we got around these by using open source data to build and kind of prove the concept of the model. So then it could hopefully be applied to more useful data sets. So we adapted the scope of our project to look at violent crime and associated indicators. What we did, we undertook a lot of scoping to identify what is out there. we drew up a reference matrix of what we had, what it measured, and ended up using police force, generated crime data, and ONS data, which required a lot of pre-processing, and we built that into the model. So coming onto the model, we decided to use Python and various spatial analysis packages, set up an environment and focused on those variables related to violent crime. And what I'm going to do is show parts of the model in order to display the results we were able to achieve through using just open source data. And the first stage is just pre-processing, which I won't go over. Basically gets the raw data to a stage. It can be used in spatial analysis and mapping. Involves joining the data to cleaning the data and joining to a shape or a geometry file. We used LSOA as the area unit as well as police force area. And for the violence data set, we additionally control for population variation by converting to the rate of offence per 1,000 population. Sorry, I think that's supposed to be that workbook. Visualization is kind of our second stage of our model, where we use the data generated in the processing stage. And for point data such as this, we added kernel density estimation plotting, which kind of simplifies the point data to help identify concentrations of offences when it's not so clear on the scatter map. And the bandwidth used here is important we realised, to avoid erasing meaningful clusters or obscuring them with too much noise. We did a little bit of basic time series to compare change over time at the basic level, but also using subplots, where we've used the same map classification scheme to compare data sets on firearms offence rate over 4 consecutive years. And with choropleth mapping, the way you classify the groups, these kind of groups here, kind of impacts how we interpret the maps. So comparing different classification schemes and how they fit can be important. Here are 2 classification schemes, Quantiles and Fisher-Jenks side by side, just to visually show the difference. So what we did was we generated objects for the different classification schemes using map classify and compared the fit of each one by plotting the ADCM score, which is a measure of fit. I think it's how compact the classes are. A lower number is a better fit, which helped us obtain the optimum fit for a particular visualization. I'm going to move on to the third part of our model that undertakes some spatial data analysis. So for this one, we just extracted the Merseyside LSOAs from the Northwest Region violent offence rate dataset. And visually, we can already identify some potential hotspots with high offence rates. But if we're going to be using this in assessed reporting, ideally we want to be able to give some statistical certainty to these kinds of observations and avoid seeing patterns of clusters where we want to, because we can be biased by our local knowledge or the intelligence we've seen. And the first step is to look at a test for spatial autocorrelation. We used Moran's eye. It involved creating a spatial weight subject that indicates if 2 areas are neighbours, and pair it with a spatial lag variable, which measures the similarity of attributes between areas. And just to show them side by side, the spatial lag variable on the right mapped out, it shows, compared to the original map on the left, shows how it kind of acts as a smoother, and the clustering becomes more obvious. So the Moran's eye test provides a correlation statistic, which is easier to understand when it's plotted against a reference distribution under the null of complete spatial randomness here. And our statistic, which is the red mark, is outside of that, which shows there is spatial autocorrelation in the violent offence rate. We can also check the significance by, we also generated a pseudo p-value, which again confirms significance. And then we tried to identify hotspots, cold spots, and outliers by generating Moran's-I for every observation in the data, and create a LISA plot, which is stands for Local Indicators of Spatial Autocorrelation. What we did here was identify the 228 LSOAs where there's a significant p-value and plotted them on the Moran scatter plot, and then shaded them according to their statistical significance. And this is what helps us identify the statistically significant hotspots. The red ones, for example, are high offence rate hotspots. And then we can plot these on the map to highlight where the statistically significant clusters actually are, and also how it compares with the original map. So what we've done is use some statistics to describe how the violent offence rate variable clusters in space and whether or not that clustering is significant. And what is the expected impact? Well, we used open source data to build the model, which has its limitations in terms of being able to draw out new or useful insights. However, this type of analysis and incorporating other data could feed into Home Office, hotspot policing initiatives, or help forces obtain GRIP funding, which is additional funding to force us to support short-term suppression of serious violence or longer-term strategies in hotspot areas. The potential for using unrestricted data is also there because, as I said, spatial analysis is a big gap within intelligence assessment at the strategic level. And giving statistical certainty to visual patterns is really useful because we can describe our results with what we call measured confidence in intelligence analysis, which impacts how much value we give to a statement when using it to form insights or recommendations. We already have a lot of interest in this type of modelling within the illegal commodities, at least, which include firearms and drugs, because it isn't being done or used in this way. So there is a lot of potential for using in an assessed intelligence reporting. And that is our project. Happy to answer any questions you may have.
Brilliant. Thank you very much. And that was really fascinating and a great demonstration of, I mean, maps are always great. I think they're great visualizations of this kind of stuff. And it's really, really nice to see how you've used that in order to tackle a really important problem that I would argue sort of spans the policing and the healthcare sectors. So I think it's a fantastic demonstration of why we do what we do in terms of integrating policing and health and social care research. So fantastic to see that, and lovely maps. I say I always love seeing maps. I'm going to kick off in the first presentation of this batch with Richard and his team, who've been looking at the 111 service and trying to look at meeting the demand for 111 and specifically looking at primary care services. So some really interesting modelling that he's done that he's now going to talk to you about.
All right, thanks Dan, and welcome everyone. Yeah, as I say, I'm presenting this on behalf of a couple of my HSMA course mates, Maddie Smith and John Green. Looking at modelling the demand from 111 for primary care services. So about half of the sort of 19 million calls that are made to non-emergency 111 telephone service in England result in a primary care disposition. That is, either the patient is advised to contact their own GP or a request is made to a primary care service by 111 to contact the patient directly. However, there's been little change to commissioning arrangement for primary care to actually meet this kind of new demand from 111. And the concern is that if a timely service can't be provided to patients, actually they may seek alternatives themselves, such as calling 999 or attending the emergency departments directly. So the sort of two questions really we set out to address was, one, to see whether actually is it possible to create a model of the healthcare system as it relates to these callers, and if we can do that, then perhaps we could adjust reality and say, well, on the if we could make it so that callers always received a timely provision of primary care service, would that actually lead to a reduction in avoidable emergency department attendance? And Dan touched on some of these operational research methods, but essentially we use two of them. We use network analysis and we use discrete event simulation to help us do that. We also were fortunate that the Yorkshire Ambulance Service have been not only run the 111 service for Yorkshire and Humber, but also have been contributing data to the Connected Yorkshire data set, which comprises of over 1 million patients in Bradford and the surrounding area, and essentially has linked ambulance service data, 111 data, and primary care data sets together, which kind of makes it more straightforward, certainly won't say easy, to actually follow patients as they sort of transit through the healthcare system. And we were interested in what happened to them in the 72 hours following that initial 111 call. So the first step to a discrete event simulation is actually to get a pen and paper out and actually create the model on a piece of paper by engaging with stakeholders and people who really understand the system, as well as just doing some preliminary data analysis to actually kind of try and spot the patterns and define the kind of relationships between these systems. And that obviously was quite challenging because we didn't really understand the data that well. And it turns out, while there are relatively few components in this particular model, they can all interact with each other in two ways, which made it actually slightly more problematic than we anticipated. But some of the early work we did meant that we could actually generate process maps. You've seen some of these already, where actually we could see patients. Each one of these dots is essentially a patient who's called 111 and been given a primary care disposition. And over here is that's the index. It's IUC, which is the integrated urgent care, which I'm using synonymously with the 111 telephone service at YAS. Over here is GPs, which is where everyone should be transiting in theory. But actually, we're seeing that trickles of patients are coming out of 111 and going to 999 or going to their local emergency department, for example. So already at quite a high level, we had an indication that actually patients are transiting in different ways than perhaps is anticipated. They're also, in some cases, spending quite considerable time in that system, rotating between different healthcare systems. And bear in mind, this is literally only a 72-hour period. The other issue we had was actually really, while the model is fancy pants, SymPy, coded in Python, and there's been lots of blood, sweat and tears, for consumers of this data, they're not really that bothered. And we needed to find a way by which we could communicate our findings in a way that those who are not necessarily technically qualified could actually understand the data. And so in order to sort of start that journey, we developed a dashboard, which essentially is just a web page, but behind the scenes is powered by Python. And so the user can actually specify how they want the model to run, and then they can actually look at the results themselves. So I'll just briefly just show you that now. This is effectively it. At the moment, it's quite basic in terms of the configuration. You can specify when the simulation should start, how long the simulation should run for, and the number of runs. So because the kind of model underpinning this is based on sort of distributions of data, which are then randomly sampled from, you can hopefully capture some of that kind of stochastic random nature of the real world in the model. But it helps to actually run the model multiple times and then kind of aggregate the data to get a more accurate picture of what's going on. And then the other advantage of discrete event simulation, of course, is that we can actually suspend reality and we can ask what if questions. What if we changed how the system worked and did something else? And in this case, our what if scenario was, what if actually every caller who came in to 111 with a primary care disposition actually did have a timely contact with the GP? So some of the preliminary results, and this is sort of really much, this is very early stages still, actually looked at comparing the real Connected Yorkshire data with the model data. And we can see actually in terms of the total numbers, it's fairly close. The model is currently overestimating the number of callers that are coming into the system. But in terms of the kind of first low hanging fruit, which is actually what is the first activity that a patient's receive, or which part of the healthcare system do patients access after that initial call, we can see they match pretty closely to the real data. And the first thing that obviously really leaps out is that over half of these patients do not have any healthcare system access within 72 hours following a triage disposition of contact or speak to a primary care service. In order to get to this point, we actually had to undertake a network analysis to really map the relationships between these various healthcare systems and how patients can transit between them. And what we see here in comparison to perhaps some other network analysis is that this is a two-way process. You know, patients can go from the index 111 call, represented here by index IUC. They can go to 999. They can't come back to that index call, but they can certainly call 111 again, or they can go to the emergency department and then come back to their GP, or perhaps come back to 111. And so network analysis is really useful when we were capturing this to enable us to estimate those kind of the probabilities that if you were at an emergency department now, that your next step might be to go back to your GP or call 111, or actually just exit the simulation because those 3 days had expired. But for an individual patient, we really kind of wanted to sequentially track their journey through the model. And the way we did that, just visually anyway, was using a Sankey diagram. So on the left-hand side, we have that kind of index 111 call. We can see quite a healthy number here, just exit the model, i.e. they do not have contact with any healthcare system. But as we have a look through here, quite a few patients actually do have multiple points of access of the healthcare system. If we look at this column here, for example, that's suffixed with a 5, that means that these patients in this group have had 5 healthcare system interactions. Bear in mind, this is in 72 hours. And while it is a minority of cases, that still represents around 2,000 individual patients. And obviously there are a handful who get into double figures, who spend 3 days literally going from pillar to post. And so there's some interesting work around actually determining why that might be occurring. So this is back to the real data. So there are a little over 71,000 index 111 calls. And as I kind of pointed out before, over half of those actually just disappeared. They vanished. They were nowhere to be seen in 72 hours, which either meant they did not or could not access the healthcare service. We did see just under 2% of patients who went straight to 999 as the first action, and just under 5% of cases where they presented at the emergency department as their first healthcare service interaction. With respect to those kind of avoidable attendances in the emergency department, what we saw from the basic model is that actually it would appear that if you have timely contact with a GP, then actually there's a slightly higher percentage of cases that will end up with an avoidable attendance, 14% versus 11%. When we then looked at that kind of altered reality, when we only considered patients who, that we considered all patients who received timely contact with a GP. Obviously, the avoidable attendance rate was exactly the same, but it did generate additional attendances. And actually, while this says 6,600, this is actually 3 runs of the model. So if we assume that each run the same, in reality, we're talking around 2,200 extra attendances as a result of contacting a GP. Now, at this stage, I should stress, it's not entirely sure whether that is actually the case because the model still needs some work to refine, but it's quite an interesting and maybe slightly counterintuitive or unexpected result if that is true. So the next step for the project is to continue to refine the model. There's still some work to done to kind of validate the model on, you know, the real world as it happens now, before we can have a little bit more confidence in tweaking and adjusting reality when we ask those kind of what if questions. We're also looking to further develop the dashboard to allow more sort of granular control over the model itself, including potentially enabling an end user to actually upload their own distributions for patterns of arrival, you know, to call 111, maybe adjusting the transition probabilities to hopefully make this model more generalizable and generally more useful outside of this kind of initial quite small regional setting. With respect to the impact, I think this tool is going to be able to provide insight both for commissioners and other stakeholders regarding the kind of sufficiency of the current primary care service provision to meet this kind of flood of 111 calls, as well as highlight kind of just, you know, actually how patients transit through the healthcare system or don't transit through the healthcare system. It also is going to provide a springboard to demonstrate the utility for discrete event simulation and other operational research methods to actually harness, you know, the huge swathe of data that we have sitting in our data warehouse. And actually we have a lot of pressing operational problems with no real clear solution. And I think operational research methods can really help provide some guidance for those kind of decision makings in what are really wicked problems. So in conclusion then, modeling the patient healthcare journey with respect to this particular cohort of patients, entirely possible, definitely non-trivial and not for the faint-hearted. For those of you on the HSMA 5 program, I'd certainly advise you think about your data early and make a plan, because actually this proved to took a very long time to kind of actually understand, figure out, and sort of coerce into a format that was actually useful. And the other thing, which I say is really tentative, grain of salt kind of stuff, is that actually if the primary care disposition timeframes were met, actually ED attendance would go up, although the avoidable attendance rates would be unaffected. Thank you.
Perfect. Thank you, Richard. Again, another fabulous presentation and a lovely demonstration of discrete event simulation. Fantastic to hear about your journey through that. Okay, so let's move on to our second presentation of this batch. We've got Lisa now, who's going to be talking about some fantastic work she's been doing, looking at predicting emergency department transit times at Sheffield Children's Hospital.
Hi, my name is Lisa Sabir. I'm an emergency medicine doctor currently with Sheffield. At the time of starting this project, I was working in the Sheffield Children's Hospital. And essentially my project was looking at using forecasting methods to look at emergency department lengths of stay in order to workforce plan. So the issue that we were looking at was basically to predict the length of stay or the arrivals in the emergency department at different times of day, days of the week and months of the year. The reason why this project came about is because crowding in the emergency department is a major health issue. Not least because of the adverse patient outcomes. So there's been some studies which I'll talk about that's demonstrating increased mortality, delays to giving or starting treatments such as antibiotics and sepsis, patient experience of the whole journey. If you imagine anybody that you care about or relatives that are waiting a long time in A&E isn't particularly pleasant. Adverse effects on staff, which can lead to burnout, so feeling that you can't provide the best care that you'd want to be able to provide. And then it also has a knock-on effect on ambulance waits and handover delays, and that prevents them going on to attend other emergencies. So as a bit more background, sort of this time last year, you may have seen quite prominent in the news, and this is a recent paper that was published in the EMJ, and there's a QR code link there for anybody interested. So this is a big retrospective observational study that looked over a 2-year period at type 1 EDs. And they were looking at, their primary outcome they were looking at was all-cause mortality within 30 days of admission. And quite strikingly, the conclusions was they found for patients who were delayed in excess of 5 hours from arrival to admission, there was a linear increase with respect to mortality. And probably that last line there, for every 82 patients admitted whose time to inpatient bed transfer was delayed beyond 6 to 8 hours from time of arrival to the ED is 1 extra death, which for me is quite striking results. So moving on from the Royal College of Emergency Medicine, who are sort of the overseers of the emergency team, they've got a winter flow project that they've been doing for a few years, and essentially the left graph here is looking at the 4-hour standard, which we've heard a fair amount of it about today, and what you can see is actually 2021 to 22 were significantly lower than the previous years. The target's 95%, but actually we're not really hitting that at all, even in previous years. The right-hand graph is looking at 12-hour stays as a percentage of all attendances, and again what you can see is longer wait times compared to previous years last year, and that's likely to continue into the following year. This obviously has financial penalties for trusts associated with delays to admissions. So lots of things affect attendances to the emergency department, so rising attendances, pressures on community services, so not being able to access services in the community, mean that patients turn up to the emergency department. Hospital bed occupancy, so it's probably a big one. Patients are waiting sort of social care packages. That means that they're occupying a bed in the hospital, which means that you can't get patients out of the emergency department into the hospital, and that prevents your flow. Different hospitals have different departmental capacities, but as you can imagine, there's a limit on the number of patients you can see based on your capacity in the department. and then also staffing. So quite a lot of these factors I sort of feel like I wouldn't be able to have any influence on, but some things like staffing, I thought if you could figure out when patients are coming and when they're staying longest, could you workforce plan in order to try and minimise some of the effect of this crowding? So the two methods that I aimed to use was forecasting and machine learning. So initially I wanted to produce sort of time series forecasts to be able to explore the trends and obviously the different areas of sort of under resourcing in order to workforce plan. In order to do that, I've used a historical data set, and then the plan was to try and produce a tool that different trusts could use. And I used something called Streamlit, which I'll show you, which is an open source app that uses the Python language, and it helps you to create a shareable web app using your data scripts. And then machine learning using routine data, I chose from January 2021 to 22, mostly to sort of minimise the impact that COVID would have had, and I'll show you the graphs for that shortly. So I had some issues obtaining the data from the information governance team for Sheffield. So initially, all of the stuff I'm presenting today is actually the Somerset Trust, which is my mentor, Andy Main's trust. But hopefully we'll move on and get my data into there. So I'd recommend starting information governance forms early for the HSMA5 team. So essentially you produce a graph as the forecasting. So this is the number of patients presenting to the ED department. And what you can see here is this is the data that we actually had. This is the cutoff, and then it's just a 30-day sort of forecast here. And sort of trends wise, it's a bit of a dip here, which is COVID, and then a slowly increasing trend. And then just moving on, this graph here is the number of patients presenting. The top one is walk-ins, and the bottom one is ambulance patients. And again, probably it's by days of the week. Interestingly, sort of probably as you'd expect, Saturday, Sunday have got sort of increased patients coming in, whereas during the weekdays there's sort of slightly less, probably because there's more community services available and different methods that patients can access care. And then the next graph shows the same length of stay for patients who walk in and length of stay for patients coming by ambulance. Again, you can see the effect of COVID, so that's that dip there. Probably a small amount of an effect there with the ambulance stays, but not quite as prominent as demonstrated by the walk-ins. Probably interestingly, the thing to say about ambulance patients is this increase and sort of quite significantly higher length of stay compared to the walk-ins is probably because generally if you call an ambulance you tend to be sicker, you tend to need to be admitted, and then you need to wait for that ward bed. So I think that's probably the reason for that there. Moving on to sort of looking at that by days of the week, I think the most interesting part of this graph is that Mondays, generally the length of stay tends to be higher, and the highest, and sort of my gut instinct of having worked in hospitals is probably because we're not discharging patients over the weekend, and maybe that causes a sort of knock-on effect to your Monday length of stay, and as you get further on in the week that drops down. So like I said, I'm planning to, I've got hold of the Sheffield Children's data now, so I'm planning to input that into the forecasting model that's created, and then work out its accuracy, and then add on things like holidays, because we tend, certainly in the hospital, Sheffield Children's, we see less attendances in school holidays, and certainly other areas probably likely to see more sort of holiday destinations. So I'll just quickly show you the Streamlit app. So that's this here. So it's got a template that you can download in order to then upload it in the appropriate format. So that's so different trusts can put in their data. So you just, it's a bit of a demonstration, upload the file that you then put on, and then it will run and show the table. So this is just what I've been showing you there. So it's got the date, the number of walk-ins, the number of ambulances, and then their respective length of stays. And then you choose what you want to forecast based on what you've put in. So if we do self-referrals, you can then change the number of days. So we'll leave it to 30. and then it will show you the graph that I've already showed you before. And then again, you can change certain things about that and have a play with it and be able to sort of see your seasonality and trends. So that's that. I'll just come out of there. And then the next thing I wanted to do was look at machine learning. Unfortunately, I've not had enough time. It's been me on the project. I'm in the process of doing this, and it's not quite finished, so I haven't presented it here. But I'm happy to talk in the breakout room shortly about anybody that's interested. In terms of impact, I'm hoping that actually if we can minimise the risk of patient harm, improve quality of care that we can give. I think organisationally understanding sort of patterns in length of stay and attempting to address ways to improve these is really important. I think the forecasting plus the machine learning will hopefully have quite an impactful way of demonstrating how we can try and improve this. There's obviously financial incentives and the knock-on effects to the ambulance services. Hopefully we'll try and quicken their capacity to go to other emergencies. So yeah, I'd like to say a massive thanks to the HSMA team, having not come from a data science background. It's been a very steep learning curve, but very enjoyable. I didn't think I'd be able to produce something like this. And Dan in particular for sorting out all of the organisational factors. And a massive thank you to Andy Main, who's been very, very helpful and very patient with my "I can't get this code to work, what's happening" comments. So yeah, thank you very much.
So yeah, thank you very much. It was fantastic, and again, another fantastic presentation. And I think lovely to see another Streamlit app. For those of you coming on to HSMA 5, we are planning not within phase 1, but in phase 2 as one of the masterclasses to write a little masterclass on Streamlit. We didn't do any teaching of Streamlit for our current cohort. Our colleague Mike Allen put out a little fantastic video on it, and it's amazing to see so many of our HSMAs actually engaging with that and creating these fantastic web apps. And this really goes to the heart of, free and open source software, and a lot of them will be sharing this stuff so that others can use it. And it's fantastic to see. Okay, thank you. So any questions for Lisa, obviously do pop them in the chat. We'll now move on to our third presentation in this batch. So we've got Stephen and his team who are going to be talking about some of the machine learning work that they've been doing around trying to predict unplanned admissions.
So I've been working with Kareem and Jahangir on a project to predict non-elective admissions. So the background is that the Royal Devon Hospital in its Exeter sites moved to a new electronic health record system in 2020. And we wanted to see whether we could use the data on this new system to predict a patient's risk of emergency admissions. There were 3 elements to this project. The first one is using structured data. The second was trying to use patient notes, and the third was trying to combine the two into a more accurate data. We didn't just want a model which could tell us which patients were at risk, but also, as far as possible, to tell us why the patients were at risk. So to understand what data we wanted to put into the model, we had a bit of a literature review, and we also asked clinicians for their views. The project was going well until we had an IT rollout in our northern sites, which sort of put a bit of a dampener on progress. So for the structured model, we used 6 months of patient data to predict the risk of admission in the subsequent 3 months. We started small with the number of variables and then expanded to more. And we tried several different models, so logistic regression, random forest, and neural network. I won't explain what those are, but on the presentation at the end, there are slides which explain them. So there were limitations to the data. So first of all, as with a lot of these projects, is a very skewed data set with a low risk of admission. So around 4% of patients who we see over a 6-month period will be admitted in the subsequent 3 months. We were just looking at one hospital's data, so we weren't capturing a full example of patients' care in other settings. We're in Devon, we're not a demographically diverse area of the world. Variables are highly correlated, so examples are ethnicity and age, for example, and there are recording issues because we're using live data in a electronic health record system. Data is only recorded when patients hit a sort of workflow where those get recorded, so there was a lot of missing data. but the model did have good results. So the logistic regression performed best, but that was probably because of the way that we sort of manipulated the data to feed into the computer, with a area under the curve score of 0.78, which seems to be exactly the same one that Andy got on his model. The most at-risk patients had a 10 times average risk of admission, and we used around 50 variables in the end, but the top 6 were age, number of medications reviewed by clinicians, having a spouse's next of kin, having a full risk assessment carried out, the number of emergency admissions, and having a diagnosis of cancer. And so this is just a graph which shows, similar to the one that Andy used around showing patients ranked by risk and their admission rate. Looking at patient notes, we made a lot less progress in this area because patient notes are unstructured, so there isn't any singular one way of writing down a piece of information, and clinicians like using their own particular ways of writing things down. There's lots of noise, so patient notes cover everything from their health condition to what they're having for lunch on the ward, and it needs a lot of computer power to analyze, which I didn't have access to. However, a simple model showed some promise. So I used what was called a TF-IDF matrix, which basically weights each word in a note by how frequent it is in the note and in all the notes together, and then put that into a random forest model. It gave an area under the curve of 0.67. And this suggested that a more complex model might provide better results. Similarly, trying to explain why certain notes were being flagged as high risk met similar computer problems. And combining the two models, initial run-throughs did improve the area under the curve score, but then when trying to tinker with it a bit, met lots of problems with overfitting, where the model got to learn the training data very well, but when we applied it to the test data, the accuracy plummeted. And at this point, this is where work pressures kicked in, and it sort of ground to a standstill. So the next steps are we're looking at using this project as a proof of concept, both for this project as a whole, but as using data science in general, and trying to find specific use cases for this data, because it's a very general model, trying to find particular teams which benefit most from this data, and also looking at how to make this data accessible to people who are making decisions. So general reflections, we do have the data to make interesting findings. Sometimes those findings seem a bit counterintuitive, but they're interesting. The more old-fashioned models, such as your logistic regressions, can be as good as your more fashionable models like neural networks. To really make use of the data, it needs a lot of resource. Working across organizations is hard. So Jahangir works in a different organization to myself and Kareem, and trying to get information governance sign-off for this was really difficult. Talking to other colleagues generates a lot of excitement, but getting regular engagement to progress these projects can be hard, particularly when you're having an IT rollout. But it has generated positive conversations about how to apply this sort of work in the future. And that's my presentation.
Fantastic. Thank you very much, Stephen. Again, a lovely project that shows a lot of potential, I think. And I love the fact that, you've started to explore how using natural language processing techniques to try and unpick some of the stuff that people write, the clinician notes can actually seems to be indicating that could help, that's starting to improve things a little bit. So it'd be fascinating to explore that a bit more. I think there's so much. One of the reasons I think natural language processing is such a exciting area for health data in particular is that it's so untapped, and for so long and for so many years the data has been, well, we can't do anything with that. It's free text data, and so it's great to see that we're starting to see methods that allow us to tap into that. Fantastic. Thank you very much. Okay, so the last presentation in this particular batch, we've got Glenn and team who have been looking at some geographic modelling around cardiac patients in the southeast.
Hi everyone, I'm Victor, and today with me are my colleagues Glenn and Janine. We also had another member, Antonia, but she isn't with us today. Sadly, she moved jobs several weeks ago. We also want to give a mention to our mentor, Adam Skoll, who helped us at several stages of our project. So our project is titled Reducing Travel Times to Treatment for Cardiac Patients in Southeast England. And this whole idea of moving care closer to home has been quite a high priority for many NHS commissioning bodies for a while now. It sort of started back during 5-year forward view. And through this reduction of travel times for patients, it can improve many aspects of healthcare delivery. For example, patient satisfaction, improved cost savings and financial spend to health outcomes. Initial scoping for our project initially focused on all cardiac activity, but we later honed this more specifically towards cardiac valve procedures in the Kent and Medway CCG region. And Dan's already talked a little bit about it already, but we've built our presentation in Streamlit, which is a very powerful tool, and we recommend it to anyone. It's very accessible, and for anybody familiar with R, it's sort of the equivalent of an R&D Shiny combination.
So we use Routino, which was an open source road network routing library based on OpenStreetMap. And the important thing to note about Routino is that it identifies the quickest route based on real roads and considering road type, not just distance on a map. So here we've got a summary of the mean travel times nationally based on the Routino data, and we can see a mean travel time of 36 minutes and a median of 27 minutes. So we've got a chart here below which shows, you can see that the rural areas have the longest travel times, and then the areas with the cardiac centres seem to have the least travel times. We also plotted this on a chart like this, and you can see that there is kind of a correlation between the population density and the travel times, with London being on the right with a large population density, and Cumbria and Cornwall top left. In terms of Kent and Medway, they appear to have a much higher travel time based on its population density. So their population density is the third biggest based on 21-22 data, and the travel times look to be slightly higher than we would expect.
Okay, so our project is about looking at what are the options, how we might reduce travel times if we have additional sites or sites available within the area. Currently, the Kent and Medway patients are overwhelmingly going into London, in particular the two sites here at St Thomas's and King's. And so we look at what would happen if we had other sites at 7 other possibilities within the area. And these are the locations which have an existing adult critical care unit, so would be suitable for consideration. Travel times at present show, so here's the national median time of 27 minutes, which is a sort of threshold which we're using for consideration here. At present, the times are overwhelmingly greater than that. 98.7% of journeys currently are greater than that. We can look at how those travel times are distributed geographically across Kent here. So we're seeing times 90 minutes plus over here in the east, and quite a bit lower where we're closer to London. And it's just this small area here where we currently have travel times which are less than the national median. So what our project is about really is seeing what happens if we have additional sites. And so in the background here, we can recalculate the minimum travel times. The Python code in the background is doing all that. I'll just zoom in. So here we're looking at if we have an additional site at Darrant Valley in Dartford, and comparing what would happen if we had an additional site in Tunbridge Wells. So for Darrant Valley, this is taking the median travel time quite close to the national median, but not quite there. Less of an impact here for Tunbridge Wells. The new travel times here, so we're still looking at 70 minutes plus for a few journeys over here in the Far East, and the darker areas here where it's been reduced to much less. And the impacts we can see is much greater across the north here for this particular additional site here. And if we put the site in Tunbridge Wells, then there's a much bigger impact here in the southwest and very little impact up here close to London. And these are the areas here where we have the site would successfully reduce the travel times to less than the national median. And we can consider each of those options against a number of different metrics here. So in particular, how many patients would have their travel times reduced to less than the national median, or what the new maximum time would be, and some others. And all the options are ranked out of the possibilities here. And from these, we see that the Darrant Valley option would be a better option in those cases. And we can add in some extra sites as well and recalculate. So I'll put in Canterbury for the first one, and add on William Harvey and Ashford for the second. And so this recalculates all of the journeys, choosing the minimum. And see, adding Canterbury here does take our travel time less than the national median here. Adding Ashford here doesn't quite take it to that threshold level here, but it's very close. And again, we can see what the travel times would be. So we've still got a few 50-minute journeys from the south here, or up here in the east. And lots of big impacts here in the east where we have the longest times, and across here, across the southeast. And here we're seeing the much bigger areas where we would have the travel times less than the national median. And again, we get the ranked comparisons on all of those metrics, and we can see that Darrant Valley plus Kent and Canterbury is a better option in those. And we can look at any of the options we have available here and recalculate as much as we like. And let's have a look at the conclusions from this.
Great. So in terms of the conclusions, we analyzed the best configurations in terms of improved travel times. We looked at combinations of a new single solo site and 2 additional sites. And what we found is that with only 1 additional site, that the best one will be placed at Maidstone Hospital. So if you look at the density plot here of travel times, we would have a reduced median travel time from 55 minutes to 25 minutes, which you can see from the movement of the blue vertical line to the orange vertical line. So it's very significant. And you can see how it impacts specifically in each LSOA in the maps below. And it's quite noticeable how travel times are, reduced for literally 100% of kind of Medway patients based on prior secondary care activity. And if you look at the our final Cloudbreath map, then the travel times are now for 60% of kind of Medway patients below the national median based on prior activity. We have a mean travel time reduction down to 33 minutes. The total travel distance reduction would be around 120 kilometers, and the new maximum travel time would be only 60 minutes when it was up to 2 hours previously. So for 2 additional sites, the optimal configuration would be 1 for Maidstone Hospital and 1 for Canterbury Hospital. There's still a bit of a change from 55 down to around 20 minutes, but the change isn't as great as just having a single solo site at Maidstone Hospital. So you can see how there's now 1 additional cardiac valve center, 1 in sort of like the center left of Kent, and 1 in center right. Again, travel times would be reduced for 100% of Kent and Medway patients based on prior historic activity. But what's probably the most significant now is if you look on the final map, then travel times are now below the national median for just over 85% of Kent and Medway patients, which you can see in the darker blue LSOAs. But there are still some regions, and particularly around South Kent, for example, which still remain slightly above the national median. And now we have a mean travel time reduction of around 40 minutes. The total travel distance reduction will be around 135 kilometers. And the new maximum travel time is now down to 45 minutes. So there is a slight change for having 2 additional sites, but we've shown that even with just one single new site, and that's already quite a significant factor in our metrics, which we had a look at. So also the applications for this method using Routino, it's not just limited to heart valve procedures. You just need the right data, which is spatially labeled. That's it. Thank you. And we'd also like to give some acknowledgement as well to everyone, to the HSMA team who've assisted us, and also particularly the baritons as well, who've helped to disseminate our work to the wider Southeast commissioning region.
Fantastic. Thank you. Thank you to all 3 of you. That was fantastic. Again, another lovely demonstration of how both maps and a web app can be used to create a fantastic tool that can really be used to look at different scenarios. And I think, you know, those kind of savings, particularly I was struck by, you know, just how significant those savings were just with one additional well-placed site, could make a huge difference for cardiac patients. So I think that's an amazing use of geographic modelling, and a fantastic way to present that information in a really engaging way. So fantastic, well done. So we'll move into our final batch of presentations now. So we'll kick off initially with Charlene and team who have been working in the Southeast looking at some of the COVID-19 vaccination demand and capacity issues. So over to you.
Like Dan said, we're here to talk to you about our project on the Southeast Regional COVID-19 vaccination demand and capacity modelling. Bit of a mouthful. So working on the project was me, Charlene Black, and Adonis Satoli, Edward Chick, and Maya Dahoki. And our mentor was Matthew Dory, who's been great and very patient with us all. And today you'll be hearing from myself and Adonis. So Adonis and I both work for South Central and West CSU, which is an NHS organisation. So when we found out we're both from the HSMA, we decided to find a project to work on together. We talked through a lot of options and spoke to a few people about how we could help improve, enhance what they were working on. But the one that shone through for us was this demand and capacity model that the Southeast Vaccination Programme modelling lead had created. So the model was created in Excel, and it aimed to predict where demand would be and where there would or wouldn't be enough capacity. And as the model grew, it became quite cumbersome to update. There was a lot of laborious copying and pasting, manual updates, and obviously new cohorts were becoming eligible, and even increasing pace, and the speed and stability, ease of use and scalability of the model was in jeopardy. Therefore, we decided to see if we could create the model in Python to replicate what it does and produce similar outputs with less input needed from the user. The potential impact of this would be better information to target improvement areas of concern, significant savings in cost and staff time, as well as making adding new cohorts and demographics easier, which would help strengthen the vaccination programme. The first step we took in the project was to spend time getting to understand the current model, and we did this by talking to the modelling lead and other stakeholders. This was a vital step in getting to understand the intricacies of the model. From these conversations, we were able to determine a list of assumptions about the model that we would need to be aware of and possibly incorporate into our version of it. Some of which you can see on this slide. There was a lot more, so it's quite complicated. So after this, Ed then created this logic diagram of how all the different Excel tabs interacted and fed into each other to give us a better understanding of the task ahead. We then got feedback again from the modelling lead, which led to this second one, which is obviously slightly clearer, but still complex, and shows how many variables there were for us to think about. Once we had a better understanding of how the model worked, the next step was actually trying to get the data to input into the model. The vaccination data is stored in the NHS Foundry system, which is understandably very restricted. And this meant we encountered a few hurdles when it came to getting and using the data. The first hurdle was obviously ensuring that everyone had access to all the data that we needed. And when we finally sorted this out, we faced the issue of how to download the data, as there's so much data and there's limits on how much you can download in one go. So it meant it was a very slow process. And it was also restricted on how we could share the data once we'd downloaded it. So it meant everyone downloading the same data. So we could get started on actually modelling, we decided to just work with small amounts of data with the intention of adding more data to help test the model once it was up and running. So I'll now hand over to Adonis, who will take you through what we've done and learned from the modelling part of this project.
Thank you, Charlene. So demand and capacity modeling is driven by the ability to understand historic activity and being able to predict future trends. This is why we chose focusing techniques gained from Module 9 of HSMA 4 to help us explore the vaccination data currently in use. My colleague Ed Chick prepared the next few slides that I'll be presenting to you. He's currently on paternity leave. The last part of my presentation will introduce our proposed interactive Python demand and capacity forecasting tool, which is a dashboard that's interactive. So the time series in Figure 1 was created from weekly data held in the Excel demand and capacity modeling tool, covering first dose, second dose, and first booster vaccination uptake for the Southeast region. Figure 2 splits uptake by dose, and then Figure 3 shows that each integrated system in the Southeast of England exhibits similar uptake pattern. Since the existing weekly dataset did not exhibit seasonality and was therefore not suitable for producing a forecast, daily data shown in Figure 4 on the next slide was extracted directly from NHS Foundry for the HIWO system. So that's Hampshire, Isle of Wight system only. We couldn't take all the systems because there would be too many rows of code as Charlene has just outlined. However, Figure 5 shows that seasonality is still not in evidence using the daily data. So the seasonal decomposition we have in Figure 5 closely resembles the 7-day moving average in Figure 4. Although it was unlikely to produce any useful insights, each technique covered in the lecture activities was implemented using the daily vaccination uptake data. Please see Figure 6 showing the naive predictions, and next to it is Figure 7, which presents the seasonal naive predictions. In Figure 8, which is on the next slide, we add the upper and lower control limits, so the prediction intervals, so that's 80% and 90% prediction intervals. So at this stage, we then changed our focus from classic methods. Figures 9 to 11 on the next slide, they summarize the use of Facebook's Prophet library in forecasting vaccination events in the southeast of England. Since there's no real seasonality over the time period in question, Prophet has only been able to vaguely pick out the general trend, which can be seen in the downward curve of the blue forecast related plots in Figure 9. Figure 10 shows us the general trend over the time period as identified by Prophet. So it's a decomposition of Figure 9. In Figure 11, if a holiday was added by Prophet, it corresponds to the date when there was a massive pre-Christmas 2021 drive for people to get a booster vaccination. So based on our explorations of the data, we concluded that there were not enough data points to see seasonality. If we move to the next slide, Charlene. So in the first few years, demand is all down to vaccination rollout, the vaccine rollout. Then in the future, we may see seasonality with annual booster uptake. So if we go to the next slide, please. I'll now summarize the key features of the Python dashboard that we are developing. This is the tool that we believe is going to replace the Excel spreadsheet. Its main purpose is to show historical and future predicted values as cumulative daily and weekly totals It is dynamic, interactive, and designed to support the NHS team to explore different demand, capacity, and supply metrics. This forecasting dashboard has 4 major components, which are the headline figures on the left, a table of data in the middle, and we have line and bar graphs for each variable of interest in the upper right section. Maps of the chosen geography are shown in the lower right section, and then users can toggle between region and integrated care system. It will be accessed online, refreshes automatically when new data becomes available. It can be adapted to complement or replace struggling Excel spreadsheets through the use of free and open source tools, most of which were gained through taking part on the HSMA program. The libraries that we are using are spelled out on the next slide. So pandas, matplotlib, and scipy, we take them as the holy trinity of Python data science. Then plotly and dash are the ones which help us with interactive visualizations targeted for the web. Dash is for assembling our online dashboard. We've put all our code in Jupyter notebooks and the documentation as well that accompanies the tool that we're building. Facebook Prophet is another forecasting library that we have used, as you saw, from figures 9 to 11, and it's relevant for insights on vaccine forecast evaluations, trend analysis, and changes in seasonality. Over to you, Charlene.
Yeah, so yeah, despite not quite being able to reach our end goal yet, we've still found like HSMA very useful and an interesting experience. Before we started the programme, most of us knew very little about operational research, data science, and machine learning and artificial intelligence. We now have good understanding, and I myself have actually used some of this, some of the things we've learned in my work. And becoming more familiar with open source tools promoted by the HSMA programme has been useful in helping to build some value-adding models that can be easily adapted to other scenarios within the NHS, obviously without the expense and restrictive licenses of commercial software. We've also been able to grow our professional network through interactions we've had on the programme and have gained a new confidence in engaging with clinicians, subject matter experts and other stakeholders to improve patient experience in the NHS. And we're all very glad to have been on the HSMA programme and are looking forward to see where the skills we have learned take us. So thank you all for your time, and we're very happy to take questions in the break or the chat.
Fantastic, thank you very much. Again, another fantastic demonstration of some of the power of the skills that we feature in the program. I think a lovely demonstration of how I mean, one of the things that we first say within the HSMA program is step away from the spreadsheet, that unless you're doing finance, you shouldn't be using Excel. And I think this is a really nice demonstration. You encountered a model that had been developed in Excel. Its limitations had quickly become exposed, and you've worked to translate that using your new skills into a Python-based framework. So fantastic work. Thank you. Okay, so let's move on to the next one. So we've got Katie and team now who are going to be talking about another discrete event simulation, this time looking at the cognitive behavioural therapy pathway in an IAPT service.
So our project is using discrete event simulation to model the cognitive behavioural therapy pathway within an IAPT service. So my name is Katie. I work in Dorset Healthcare and I am a CBT therapist, so I'm in this pathway. We also have Hannah who's helping me to present today. Don't know if you want to introduce yourself, Hannah.
Hi, I'm Hannah. I'm an IT technician in Dorset Healthcare.
And we've also got Matthew and Andrew who've been working on the project with us. And we've got Matthew here today. I think Andrew couldn't make it. And it's not on here, but Tinika was our mentor. And yes, lots of thank you to Tinika. So just to explain a little bit about the service that I work in. So it's an improving access to psychological therapy service called Steps to Wellbeing. We run across Dorset and Southampton, but for this project, we focus specifically on the urban Dorset area, just because it got a lot more confusing if we were looking too large. What would normally happen within our service is a patient would refer in, they would have an assessment, they would either be discharged or signposted somewhere else, or they would go forward for a type of CBT that we offer or counselling. They then might have further treatment or they would be discharged. We do have national targets for our waiting times and people being seen within a certain amount of time. And at the moment, our urban waiting list is continuing to grow. So over the last couple of years, it's gone from about 500 to now being 700. And the patients currently in treatment is about 750. So I've highlighted high intensity CBT because that's the part of the pathway that we are going to be focusing on. And that's because currently that does have the longest wait between assessment and treatment. So again, just to briefly explain a little bit about what would happen if they are going forward for high intensity cognitive behavioural therapy, they would either be sent through to an agency to access online typed CBT, or the therapists within our service would offer either an online group that they would attend, or there's one-to-one CBT, and that's available virtually or face-to-face. Now, since the pandemic and all the changes with COVID, we are running much more groups now. We have fewer therapy rooms that we can actually use, and we have fewer face-to-face evening clinics. We have one running at the moment, but we are slowly starting to, change groups to more face-to-face and looking at how we can do that. The average wait for one-to-one at the moment is about 6 to 9 months, so it is over the targets. There are shorter waits if patients are priority, they're going on a group, or they're going forward for online CBT. And we're estimating or predicting that the longer waits will be for patients who want evening and face-to-face appointments, because that is more limited at the moment. So that is the question that we were looking at from this project. So what aspects of the pathway are having the greatest impact on waiting times? And also looking at how we best allocate a therapist's resource and time so that we can improve the waiting list as much as we can. So what if we did change an evening group slot, which is run by 2 therapists, to a one-to-one face-to-face evening clinic? So that's the question that we were hoping to ask by using this model. So we were using discrete event simulation in Python. We were trying to create a model of the current waiting list and pathways for treatment. So the patients were passing through the model. We used a 2-year warm-up period because the waiting list doesn't start at 0 every day. And we ran the model for a year. So that's what we were looking at with the data. And we used appointments as the resources because it got really complicated if we were trying to use things like therapists or rooms or things like that. So appointments was the way we ended up doing it. And we were thinking about things like, what percentage preference do people want? Face-to-face, virtual, group, the online appointments. What percentage do people want evening, face-to-face appointments? How many groups do we currently have? Who's priority? And things like attendance rates and dropout rates as well, because generally it's higher for groups, so that might also impact things. We do have access to a lot of data within IAT. I thought it'd be a lot easier to get the data for what we were using. It turned out to be a bit more tricky, but yeah, we have data from people currently waiting and also people who have waited and had treatment as well, and that's where we were kind of using for our model. So I'm just going to switch over to the model, and Hannah's going to introduce you to it.
So this is the tool that we've developed, which we hope that Steps to Wellbeing are going to be able to use going forward to look at different sort of resource allocations and different types of appointments they could offer, and just see how that might impact their waiting times. So in the menu on the left, you've got all the different variables which are customizable. So the defaults are based on the data from the real world. So what was the situation that we're seeing at the moment? And then obviously they will be able to change those to reflect sort of any changes that they're planning on making or thinking of making in the service. So you've got all different types of appointments available and stuff in that column. So if we scroll down a bit, so the models run over the course of a year. And then, so these are the number of patients that have been seen, so patients who have reached the end of the waiting list and then started their treatment or potentially even finished their treatment. So these are the mean wait times for each different type of appointment in weeks. So if we look specifically at the one-to-one face-to-face evening, you can see that they're waiting about 29 weeks. And then on the other tab, we've got the same data, same statistics, but for the current wait list. And then a bit further down, we've got some graphs showing the number of patients waiting over time. And you can see for one-to-ones, it is steadily increasing, which does reflect the real life situation. And then just a bit further down, we've also got just raw data, just in case anyone wanted to do anything with that, or just to help us when we're looking at the model as well. So Casey's now going to change. She's going to take away one of the evening groups, and she's going to change that to be a face-to-face evening clinic. So that's increasing 4 appointments for the face-to-face evening. So that's just going to run now. It does take like a minute or so, but it's not too long.
We've met with the stakeholders, so the managers within my service quite a few times to get this sort of something they can actually use, and we do have data teams within our service. So we know that our service runs a bit different to, say, rural Dorset. They have more face-to-face available at the moment, and also their preferences are different. So a lot more patients there seem to prefer face-to-face. So that's why we have a lot of things that you can change on the left-hand side, because the preferences are going to be different in different areas there. So we met with them quite a few times. We've tweaked things for it as well. So this is the change, isn't it?
Yeah, so we can see that having changed that evening group into an evening face-to-face clinic, it has reduced the average wait time for the evening face-to-face patients. So it was 29, it's now 25. So from this, it does look like there would be an improvement. Obviously, we do still have some work to do in terms of like confirming accuracy and things. But you know, this seems to be going okay.
Yeah. So that is one of the things, if we think about what we did find out, we are still looking to tweak this model, because we've run it lots and lots of times now, and you know, there are a few kind of bits that we need to still look at, but generally it does seem to be going with our predictions that the longest waits in treatment are for evening or face-to-face. It actually looks slightly different this time around, but generally it is a higher number for those ones. So we also, you know, from asking that question, we've seen that it does seem to improve wait times by changing that evening group to a face-to-face clinic. So that helps the team that I work in to, you know, think about decision making and how can we start to do that if it's going to be helpful. So thinking about sort of learning and problems that came up during this project. So as I mentioned earlier, it was difficult to get accurate data from current wait lists. Turns out some patients don't express a preference until they're on the phone being booked in. So actually going through and trying to pull that data, I had to dig around lots of different areas and use current and past. And that happened with a few of the other things that we were looking at as well. So also the fact that we haven't really had any previous experience with coding. I don't work in data, so this is not, you know, my area. So it's been a really big learning curve, and we're still learning stuff at the moment. And we are still meeting with stakeholders. So some of the things that we are looking to improve on with the model is to build in multiple runs and then having like an average score come up. So running that model several times over to try and, you know, get an average score. And also we would like to be able to have a side-by-side comparison of, you know, the model as it looks, as the waiting list looks currently, and then when we make these changes to the resources that we have, what does it look like then? So that's kind of where we're aiming to get to. It would have taken a lot longer to run that in the presentation today, so we have kept it shorter, but that's where we're hoping to kind of end up with it. So we do think this is something that can be used for my service, but also for hopefully other services as well. We know that within our service there's going to be expansion. We're looking to treat 25% of the population, so these numbers are going to be increasing, and we're also looking to increase our face-to-face provision and really see what patients are also wanting as well. Are they wanting to stay with online therapy? Are they wanting more face-to-face? And that's where we can hopefully use this tool to allocate resources efficiently. We are presenting it to more senior management within the trust soon, and we're handing it over to a data modelling team within Dorset as well. Yeah.
Brilliant. Thank you very much, all of you. Really fascinating and such an important area, I think, that clearly is struggling so much with waiting times. I think that having a tool like this is an excellent example of how things like discrete event simulation can really help to unpick some of that and see how things might be able to improve. So I think it's a fantastic application. And you know, you said, Casey, about how you weren't experienced in this kind of stuff before. I think it's remarkable that how far you've come in developing something like this. So absolutely, you should be proud of yourselves. I think really good work.
We can give you guys the link, by the way, I was going to say, but we just couldn't give it to you before because the runtime gets massive if other people are looking. So yeah, no,
that's good. That's a good plan. Fantastic, and hopefully we'll be able to do that with most, if not all, of the projects that we'll be able to over time. I know a lot of the teams are uploading their stuff to GitHub and various other places. So a lot of these models, hopefully, you'll be able to play with yourselves and feed in your own data. And it's part of the spirit of HSMA that we encourage the teams to share the work and share what they've developed to allow other people to either use or indeed adapt what they've developed. Brilliant, thank you. Okay, so let's move on to the penultimate presentation for today. So we've got Angel and team who've been looking at, again, another discrete event simulation, but this time looking at delays in cancer treatment.
Hi, this is Maya. I'm a service improvement and business manager at Darfur and Berkshire NHS Trust. I heavily supported by my team, Jim and Hannah, and our mentor, Luca. We are planning to look into the district model for understanding what's happening with all of the cancer patients' pathway. As you may be aware, all of the hospitals are dealing with the different backlogs for the cancer rates. And based on the national target for the treatment of cancer patients, all of the patients, when they refer to hospital for treatment, to receive their first treatment, they need to be 62 days. And 80% of them need to be treated within these 62 days. And our aim of this project is to reduce the amount of time from referral to first treatment to meet the national target for 62 days by identifying key bottlenecks in pathway. By creating this DES model, we wanted to see where is the pinch points, why performance target is being missed, and where it can be improved. In the other slide, we show the other slides. As you can see, our pathways, the cancer rate pathways, is very complicated. And as you can see, there is the day 0 to 62 days. All of the patients that are coming from the different pathways from, for example, GP referrals, A&E, or different types of that, and they are coming through the different investigations from radiology, from the hematology, and different pathways to get their first treatments and getting their investigation. And for the other slides, if I'm showing. So we want to go through these problems and hypotheses. As you could see, if we are not treating our cancer patients, it's affecting the outcome of the patients, and some of the patients, if their treatment is going to be delayed, it affects to their health, specifically the mental, physical, and sometimes it's reducing the quality of life, and it affects to their mortality rate. And our hypothesis in this study is that do we have enough resources, for example, staffing or equipment, to reduce the delays in our pathways. Angel is going to continue for this model.
Okay, so out of all the techniques we learned during HSMA, we decided to use the discrete event simulation modeling We decided to use that technique because it's based on evidence base. It enables us to better understand the process and patient journey. It's a hypothetical process, so we can create different scenarios without any harm and risk to the patients, which enables us to identify knock-on impact of changes to the service. And lastly, because it's of ease of sharing knowledge, it's built on an open source model, which is easy to adapt for different pathways. The approach that we took was we met with different cancer lead services within our trust to scope the project and discuss the patient pathway in detail. We identified different areas of concern from clinical and administrative process. We used 3 years of anonymized patient records pre, intra, and post-COVID. We worked out the delays by splitting into patient and provider delays and focused mainly on provider delays. Next slide, please. So this is a simplified version of how the model was generated, and the output of this model was the mean length of time patients waited for their treatment. So patients were generated as entities as they flow through various processes. So all referred patients will require diagnostic tests, and out of these, X% will be diagnosed with cancer and will need further investigation. And then we'll go on to have discussions within MDT meetings for their care plan, and then will eventually receive their first treatment. Next slide, please. So now we will quickly present a live demo of 5 runs of our model. Jim, if you could bring that up, please. Thank you. So while that's running, we've already prepped a CSV file to show the output that was generated from this run. So as you can see, these 5 runs shows our average time for each stage, from triage to face-to-face, straight to test, staging investigation, time for treatment, and it also shows the full pathway time from the point of referral to treatment. And our average time between these 5 runs varies between 97 days to 168 days. As you can see, it can vary depending on the complexity of the cases and how complex the treatment pathway would be. Now I will hand it over to Jim, who will talk about the challenges we faced during this project.
So I'm going to stop this. We wanted to just show you the code, and there's a lot of it. So I'm going to stop it, but we wanted to show the outputs of it. We've actually run this for 100 of the different resources, to 100 runs to get it through. So some of the implementation challenges we've had around that are people work 8 hours in a day, they work a 5-day week, they don't work weekends, so they all have an effect on time as well. Different patients will get different priorities at different points of the journey. So that was another of our challenges. Branching pathways. So if you saw in the slide 3, we've got a lot of branches. We branch at the beginning from triage, and we also branch around MDT and cycle around a few times. And the MDT challenge for us in particular was quite difficult because it was probability over probability of people left. So to use the example, if there's 100 people, the first probability test would take 49 people out and leave us with 51, and then we'd have to do a probability on what's left to get them back to try and pick out sort of the MDT cycle. So the mathematics in that was quite challenging. It wasn't sort of, it's the same each time, it's a different probability of increasing up. In terms of the results, so this is from the 100 run results we did. Really did reflect quite well on the Gloucester data that we've used. It's in days, which is probably different to what a lot of other people have done, which was in minutes when you've seen the previous days. So for triage, we expect it to be very quick. And at the highest and worst on the runs, it was nearly a full day of 9/10 of a day. But it's pocketing around sort of usually a quarter of a day to get it. So as soon as the referrals are coming in, the team at Gloucester are getting them out. In terms of face-to-face, we jump out of small decimals now into actual days that start at 100 and go down to 0 here. Again, you can see the pattern kind of straight through the middle. again, which reflects quite well what we saw out of the Gloucester data of, yes, predominantly a lot of patients are breaching the 62-day, and something needs to be done with a bit of what if analysis to bring those days down. But as you can see, a 70-day wait to get a face-to-face isn't really meeting the 2-week wait, and some of those face-to-faces obviously will be after we've done the initial first test. So overall, in terms of taking that to the pathway wait days for first treatment, we've got a diagram at the bottom here. Again, this one's sort of showing down the middle, about 100, 120 days for our process to get the patient from triage through to that first treatment. We felt this reflected quite well, and sort of the breach times on them are, just check, sort of the minimum was about 15 days breach. The maximum breach was going to take us well over sort of 50, 60 days breach. The average came in at about 40 days over the 62. So we felt, again, from doing the multiple runs, we were getting kind of close to what we wanted to do, which would take us into our next steps of what if analysis for additional resource, additional capacity, things like that. So the next steps for us, we've predominantly got something, a basis to start with. We've done a lot of analysis outside in Excel to begin with. We need to do more analysis with graphs and graphical representation that is useful to the end user, not to us. So a lot of what we've done makes sense to us, but our target really is our Cancer Alliance teams, our fellows in BI at Gloucester and Morecambe Bay, really to get this to be something visual and effective so that they can make decisions. So those are our next steps. We realize we may have to do some deep dives into multiple disciplinary process, diagnostic steps, just to understand maybe some of the weights there. We're at the stage of doing more what if. I think we've got the model to a place where we're happy that it mimics what's going on now. We now need to do our what if analysis. Very keen to share the code, and our next steps would be to do the breast pathway, which was originally on this project, but we decided to just focus on colorectal to begin with, just to get something out there. Long-term plans, both me, Angel, and I think Maya may be carrying on with this after, and we're keen to find others that are interested in this area post HSMA 4 to get involved with us in terms of coming up and discussing these things after, and if it's something that anyone's interested in joining or being involved in from a cancer point of view, we're looking to do other cancer pathways, like I say, breast being first, but skin and head and things like that. We're keen to adapt what we've got and take it forward. A few references here about how we got our data and the fact it was anonymized and where we found some of our statistics. Again, if there's any information or slide decks or code or anything you want to talk about, feel free to put it in the chat or come to us at the end of the session. Thank you.
Fantastic. Thank you very much, all three of you. I think that, again, a fantastic presentation, such an important area again, and some really promising results coming out there from in terms of what potential ways forward, I think. And fantastic to hear that you're very keen to continue this and to work with others. So hopefully you'll get some interest, and other people will sort of come forward, because I think there's a great demonstration of what we do and the collaborative spirit that we encourage. So
I suppose that the final thing we didn't say was big thank you to Luca, if he's on the call. Couldn't have done it without our mentors, and the mentors are incredible.
Fantastic. No, that's great to hear, and it's big shout out to the 11 trainee mentors that we had supporting us, because people like Luca and others who have allowed us to deliver such a large scale program and support so many projects that you're hearing about today. So we move now on to the final presentation for today. This is Irma from Oxford, who's done some fantastic work looking at discrete event simulation again, this time looking at a backlog in children's neurodevelopment assessment with extensive backlogs and hopefully some real signs of a promising way forward. So over to you, Emma.
So as you said, my project was around using discrete event simulation to tackle the long waits and the growing backlog for children requiring neurodevelopment assessments, so autism, ADHD, and comorbid. I'm from Oxford Health NHS Foundation Trust. So what's the issue? The service is not able to keep up with the demand. We're looking at Oxfordshire and Bucks, but also across the country, as illustrated in the figure, which shows the increasing number of patients still waiting for an assessment over the past 2 years. Moreover, the average waiting time has increased by more than 50% in the past year, with patients waiting more than 2 years on average. What impact does it have? The impact on patients is that children are not receiving the support required, which means a deterioration in mental state. Parents are expressing concerns and lack of support while waiting for an assessment. The impact of service is longer waiting times means longer assessments, and complaints impact on managerial time and team morale, and we are losing staff to the private sector. So I've split this in what do we actually need to know on the whole process. So first of all, we need to understand the current pathway, which was quite tricky. We then needed to identify where are the main bottlenecks, the long waits in this pathway. And then we wanted to, okay, so now that we know the main bottlenecks, how do we actually manage the ongoing demand, and what do we need to do in order to maintain a steady state and avoid a backlog from growing? And then finally, we know we already have a huge backlog. So in addition of keeping a steady state, what do we need to have in order to eliminate the backlog that has developed as a result of the ongoing demand not being met? So these are the four kind of areas we wanted to address. So the pathway on a high level is referral gets sent from GP. It goes to SPA, single point of access, will triage the referral to the NDC team, which is sends out the questionnaires to schools and parents. Schools and parents return the questionnaire. The clinician determines the complexity. If it's complex, there are several face-to-face appointments with specialists. If it's simple, sometimes there's just digital appointments. And at the end, it goes back to clinicians to feedback to parents, signposting, obtaining referral consent, and so on. So that's kind of on a very, very high level. Then we looked at, so this is the pathway in a more detailed level, which also shows now the 10% trimmed mean waiting time in days between the different steps happening. So I won't go too much into detail here, but one of the things we wanted to look at was there were issues around, well, there were some questions around how long does it take to actually return the questionnaire back from parents and schools. And actually that waiting time wasn't that big at all. As you can see, it's only 35 days compared to, other waiting times in the process. So we kind of wanted to first look at this section here. And so it's the section where the episode gets opened to NDC by SPA. And then it takes almost 2.5 years for the questionnaire to be sent out. So what we actually saw that on average 4 questionnaires get sent out per day, and it's actually an artificially induced wait because the problem lies somewhere down the line in the pathway. because there's just not enough capacity to address all the questionnaires if they send out hundreds per day or so. So by focusing on further down the line, the pathway, we would address this long waiting time here. So this is just what I said about the 35 days and the 648 days. So by focusing down the line here, we are actually looking at this pathway, and this is what we designed in the model. So just going back to the model, so we are looking at referrals with completed questionnaires arriving as 4 per day. So that's kind of the entry point of the model. And then appointments get booked, and we can see who is booking the appointments. In blue, we have the trimmed mean now in hours. And then we have the split if it's ADHD, autism, or comorbid. So if it's ADHD, for example, after the appointments are being booked, there's an average of 8 appointments that take place, and it lasts about 40 minutes. And after that, there is a final appointment with parents to feedback and then close the referral. Now, in all of these different sections, we identified who is actually doing those appointments. So for ADHD and autism, we have on average 8 appointments. For comorbid, we have 10. But the thing is that we have staffing, like we have the admins, we have lead clinicians which are non-comorbid. So these are lead clinicians who are doing ADHD and autism. We have lead clinicians who can do comorbid as well as non-comorbid. We have the second assessors who can do comorbid as well as non-comorbid. And we have second assessor who only can do ADHD. We also identified that out of those, for example, for ADHD, out of the 8 appointments, 60% are delivered by lead clinician and 40% by second assessor. Sometimes they also deliver them together, but most in the data what we saw is most often it's, the split is 60-40. Similar with autism, it's 70-30, and with comorbid 75-25. I wanted to mention that the model is a simplification of the real world. The pathway itself obviously is far more complex. There are several assumptions that I will go through later, which are simplifying the model. Right, so what changes need to take place in order to keep on top of the ongoing demand and see the patients within an acceptable time? So for this, I would like to demo the tool. Give me a second. Right, you can still see my screen, everything okay?
Yeah, that's fine.
Okay, great. So I thought I include in the tool just to show the model and the assumptions, first of all, because I think it's really important to actually have to be very clear on the assumptions. So I have summed up the staff whole-time equivalents, and I'm assuming the staff are spending 2 hours per day on appointments and are busy with other things, but at the same time. So all staff are at the same time spending 2 hours per day on appointments. And why 2 hours? That was what I saw in the data. So out of the whole data, spending actually just 2 hours on clinical appointment time. I didn't include any holiday or sick leave, and all staff are unavailable at the same time. There's also an MDT discussion that happens regularly for comorbid cases, which I haven't included, and I can go into detail later in questions why I haven't included certain things. But if I just run the current model as it stands, so here again, I'm repeating kind of the picture of the model, and I'm running it for the last 5 years, and I'm using 10 runs. We also used 100 runs, but we didn't actually see much of a difference there. So what are the charts showing here? So this is the whole journey time. So what I mean by whole journey time is from the moment they enter, the completed questionnaire gets returned because that's our model. So from the moment a completed questionnaire gets returned to the moment the referral is closed. That's what I mean by whole journey time. And then I'm splitting it by ADHD, autism, and comorbid, and it's the waiting time in days, right? So with the current research that they have, the waiting time in days, which is kind of similar to what we are seeing in the data as well. So one interesting thing I kind of saw immediately was that there is something in common between autism and comorbids, so because the numbers are high. And when I looked at overall how much of the demand they're meeting with the current research, they're actually only managing 61% of their demand. So their backlog is growing by 2 every day. So in 1 year, you're going to have 397. So that's kind of the message. But there's something interesting between autism and comorbid. So when I then looked at staffing, who is actually delivering autism and comorbid? So it's either lead clinician, any, which means lead clinician, non-comorbid, or lead clinician, both, and second assessor, both. And here it's lead clinician, both, and second assessor, both. So if I, for example, increase lead clinician, both, to 6 and run the model and see what happens there. Sorry, that takes a bit of time to run. Not too bad. So you can see that this didn't actually produce much change. So this wasn't really my bottleneck here. So I'm going to go back here. The other common thing here was that the second assessor, both, they're delivering both appointments for autism and comorbid. If I increase second assessor both to 3 and run the model and see what happens then. So remember, our waiting time was in hundreds of days. And I'm just going to look at what happens if I increase the second assessor both. So this is now the waiting time split again in days, but it's down to, the whole waiting time is down to, 20, 40, 60. I do have here statistics about the median waiting time and so on. So you can see that by recruiting just one second assessor, both, it reduces dramatically the waiting time. However, so you can see also they are managing 99% of the demand by this, by only recruiting one resource. However, ADHD is still quite high here in number of days. So if I increase ADHD, second assessor ADHD, and run the model, then I can also look at the waiting time and compare it. I should learn to talk while it's running. Right. This is now down as well. So even though they were managing the demand, even with that previous research with 3 second assessors both, the ADHD waiting time was still high. Now they're all very low. So this is what is shown by managing the existing demand. There's obviously still the backlog. Just wanted to summarize what we just saw, because I think it's more dramatic when you see it this way. So by recruiting a second assessor both, previously they managed, with the existing resource, they managed 61% only. By recruiting a second assessor, they're managing 99%. The waiting time overall, was in, I think median was about 300 or so, which is down in tens by recruiting second assessor. So that's the question around existing demand. Now, in addition to maintaining that steady state, how do we eliminate the backlog that has developed? So again, I'm gonna go back to the demo. So I'm gonna here include a clear backlog of 2,470 patients in 5 years. If I run it with the one that was great for steady state, and see what happens there. And I don't actually have 2 screens because I want it on the other screen to actually. So again, with introducing the backlog, they are managing only 58% with that resource. I actually identify what resources needed in order to manage it for in 5 years, the backlog, to reduce the backlog. So it's 52544 is one of the options. 52544, run that. But what I wanted to highlight here is that there are possibly different combinations that would help to reduce the backlog, and I would like to let services decide what the best way for them would be, because recruiting someone long-term or short-term, and it might be that different decisions might be taken place if you take into that into consideration. So we're providing a tool for the services to decide what's best going forward to recruit. So this is one of the options with this to reduce the backlog here. So I kind of wanted to go to the main challenges. So the main challenges in this project were actually not so much the technical side, but more mapping out the whole pathway. And it was, I think, mostly due to the lack of clear documentation and obviously staff and process changes and who does what, and different people do different things in the whole process. So it was also surprising to see that several sections of the pathway are not recorded in the main clinical systems, but rather in Excel spreadsheets. And then there were also a significant amount of incomplete data, which we had to deal with. So next steps, the findings and the model has been presented to the stakeholders, including service managers, clinical and operational leads, service heads, and the trust board. And discussions are already taking plans on how the model is used to support and improvement work in the service. It's worth noting that the current model is developed based on Oxfordshire and DC pathway. We are now looking into if we can implement a similar model with the Buckinghamshire pathway as well. And the tool is available to use as well to everyone. Thank you.
Fantastic. Thank you so much, Emma. An absolutely amazing story, I think, of what I love about that is that you've kind of exposed the kind of fundamental problem in the system. What was so interesting was where they thought the delay was actually, it didn't unpick the fact that there was an artificial delay in there because of the delays further downstream. And so using the modeling to really understand that, and then so powerful to say, well, actually that we can see our why this is such a mess, because the waiting times are spiraling out of control. And actually, to get that back under control, we only need one more of this resource, and that will get things back under control. And then I love the fact that you've then added in the if you also want to clear the backlog in X amount of time, then this is how you need to do it and how you need to resource it. So yeah, absolutely fantastic. I think it's a great thing and so important for so many services, I think now. So such an important issue you've covered. But just before people disappear off, I just wanted to say a massive thank you again to all of our HSMAs who presented today. I've been sat here for 4.5 hours beaming with pride. Genuinely, the work that you have all done is absolutely astonishing, and it never ceases to amaze me the amount of impact and fantastic work you've generated, and sometimes it can be difficult for you to see that, but just think back to 12 months ago when I was showing you how to print the words "Hello World" on the screen, and now you're developing tools, discrete event simulation models, geographic models, machine learning algorithms that are having real impact, and you're transforming the way in which your organizations are dealing with this. So I have to say a massive thank you to all of you. It's been a great pleasure to work with you all, and I cannot wait to work with the next cohort, but also to hear about the fantastic work that you continue to do, taking these skills forward. And a big part of HSMA, as I say, is building up this community. We've now got over 300 people on our HSMA Slack workspace, and obviously that's growing every year, and you are forever welcome to be part of that community, and we'd love to hear about the work that you continue to do and engage with our HSMAs moving forward. So a massive thank you to all of you. Fantastic presentations today, and also thank you to everybody who's come along today as well to listen. I appreciate nearly 5 hours we've been going now is a long time to sit on Zoom, and it was so lovely to see that we retained so many people for such a long time, and I think that speaks volumes of the interest levels in the presentations that have been delivered. So thank you for coming along and hearing about our HSMAs and their journeys and their learning and the impact that they've had today.